Biplab, you have joined.
Yes, joined Kosik.
Shall I make you the host now?
I'm already the host.
Oh, okay, okay. Oh, you have joined later.
Yeah.
Okay.
Good morning, everyone. Welcome to day 5 of this joint faculty development program. We are waiting for our expert. Once he joins, we will start the session.
Hello, good morning.
Good morning, Amit sir.
Good morning. So we will start from 10. Na?
Yes, sir. From 10, we will begin.
So means from 10, I should share my screen or start or some any other introduction for like this required
Yes,
from
yes,
your
yes, sir. We
side.
will be giving a short introduction of yours, and thereafter we will hand over the session to you.
Okay. And one more thing,
Yes, sir.
uh, let's say for during introduction phase, I will turn on my video.
Yes, sir.
And during presentation, can I turn off my video?
Yes, sir. You
Means,
can turn off, sir.
bandwidth issues are there
Yes,
because
sir.
so many participants are there.
Yes, sir. While during the sessions, you can turn off your video.
Okay.
Okay, sir. Very good morning to all participants and resource persons. Welcome to day 5 of this joint faculty development program on machine learning application in signal processing and communication engineering. Today we have uh, Dr. Amit Vishwakarma sir as our expert. He will be taking lecture 16 on machine learning in biomedical signals part 2. Before we start, we would like to share a brief profile of Dr. Amit Vishwakarma sir. Dr. Amit Vishwakarma sir received BE degree from Taxila Institute of Engineering and Technology, Jabalpur, India in 2011 and MTech degree from PDPM, Indian Institute of Information Technology, Design and Manufacturing, Jabalpur in 2014 and completed his PhD from IIT Guwahati in 2019. Then he worked as a data scientist for 5 months. He is at present a member of IEEE and IET societies. He has published more than 25 publications. He is currently a reviewer of various IEEE, elsewhere, Springer journals and conferences. Dr. Amit Biswakarma sir, welcome to the session. Uh,
Thank you. Thank you for a gentle introduction. Thank you very much. So, should I start my lecture?
yes, sir. I made you the presenter. You can share your slides also.
Okay. So, good morning to all of you. So, we will be discussing the biomedical signal analysis using using machine learning, specifically for EEG signals, right? So, I am turning off my video so that there is no bandwidth issues will occur. So, stop sharing and sharing my screen. So I hope my screen is visible to all of you. This PDF.
Yes, sir. It is visible.
Come to the full screen mode. Now I think I should start. So once again, good morning to all of you. So this will be a lecture on machine learning in biomedical signals, part 2. So let's discuss. So first of all, what are the different types of biomedical signals? So these actually some of the important biomedical signals are categorized into two categories basically. One is related to action potential and one is related to event potential basically. Okay. So what are the action potential biomedical signals? So action potential biomedical signals are EMG, electromyogram. Then we have a ENG, electroneurogram. Then ECG, electrocardiogram, and we have a electroencephalogram that is called EEG. Okay, so these are basically the action potential signal, biomedical signals. Now, what are the event-related ERP-based event-related potentials signals basically? Okay, these are basically EGG called as electrogastrogram, phonocardiogram PCG, carotid pulse CP, signals from catheter tip sensors, speech signal, and then we have vibromyogram VMG, orthogram VAG, and autocaustic emission signals. Okay, so these are you can see there are very wide varieties of these biomedical signals. So specifically we will because there will be too many signals, so we will target only one and we will see there are different types of methods discussed for and discussed or proposed for EEG signals. Okay, so let's discuss more about EEG. So EEG stands for basically electroencephalography. Okay, in electroencephalography or electroencephalograph signals basically. Okay, why these signals are used? These signals are used to identify the health conditions. Okay, health conditions. Now, this EEG signal actually analyze the electrical signals in the brain. EEG is a method. Basically, what we are doing, we are analyzing the electrical signals in the brain. Okay, so okay, up to this point, that is fine. EEG signals are there. So how many? Because we know there are different types of machine learning algorithms are present. So we can analyze these EEG signals using different types of ML algorithms. So there are many analysis methods are there. So but we will discuss in this presentation what some of the specific methods. Okay, and I tried to cover all the all the ML methods for analyze for EEG signal. So let's see. Okay, so one thing you have seen means from the prior knowledge that these some of the signals are analyzed in frequency domain also. Okay, means these signals are captured in time domain and we are analyzing them in frequency domain. So EEG is that type of signal which is analyzed in both domain, frequency as well as in time. Okay, so what this EEG measures? EEG measures the voltage fluctuations basically. Now, why this voltage fluctuations occurs? These voltage fluctuations are generated by ionic current present in our brain. Means ionic current present in our neurons, which are basically present in our brains. Okay, so we have ionic current which leads to the voltage fluctuation, and these voltage fluctuations are basically measured by EEG, right? So okay, so let's discuss more about EEG, and this EEG is basically means I hope all already you know means how to capture this EEG. Basically, we have the connecting electrodes. We connect these electrodes to the scalp. Okay, in scalp using and we use a conductive gel because hairs are there, so that proper conductivity is there, so we use this electrodes along with the conductive gel. So and then actually then we come to some electronic part basically, and using a differential amplifier and A to D converter we obtain the EEG recordings. Okay, and these EEG signals are basically used to diagnose the brain disorders. Now, what are the different types of brain disorders? Basically, this some such as epilepsy, okay, tremor, uh, concussions, strokes, and sleep disorders. Okay, so these are the some of the brain disorders. So specifically, we now, if any machine learning algorithm is there, so how we can means how in which problem I should use this? Actually, for epileptic seizure detection and sleep disorder, these ML algorithms are widely used. Okay, we actually captured the EEG signals associated with epileptic seizures patient and sleep disorder patients along with the healthy patients, and we actually analyzed what are the difference between the EEG signals obtained from this EEG signals affected uh, persons affected from these problems basically. Okay, so this is the one of the application. So another application of EEG is for gaming control. Means you use this EEG signal to play a game or control the game. Okay, and just means your mind is actually playing the game instead of your we are physically using hand or any physical movement. We are actually playing the game using mind, right? And this another application is basically um, to manipulate any object using your mind with some artificial let's say artificial arm or artificial leg. Okay, means you using your brain signals EEG signals to control or manipulate any machinery object or robotic arm or like this. Okay, so these are actually the current trends. Now this, if we go more on EEG, so these EEG signals have some frequency bands. So what are these frequency bands? These frequency bands are delta band, theta band, alpha band, and beta band. Okay, so this categorization is basically done based on the frequencies. Okay, so in delta band, we have a EEG signal where frequency is less than 4 hertz. And in general, it is found that at delta band, the amplitude of EEG signal is in higher side. Okay, so and what is the amplitude range of this these EEG signals is associated with some 0 to means 100 microvolt. In microvolt range is there. Okay, and then we have a theta band. Theta band is associated with drowsiness and arousal, and depending upon the person is young or older, 4 to 7 hertz. Then we have alpha band, which is actually gives you the, when we move the eye muscle activity, then we actually having the alpha band frequencies, that is 8 to 14 hertz. And then we have a beta band, which is the general motion, in which the frequency is greater than 14 hertz. So what are the advantages of these EEG signals? So first of all, it is low cost. Okay, so and if there is some, while we are capturing the EEG signal, if there are some motion is there, okay, so there is some tolerance is there for that. Okay, generally it is found that when we move, so the signals actually distorts, but there these EEG capturing device having some tolerance against the motion. And another is a very big advantage is that it is having no radiation like MRI or CT. So it is having a no radiation. So what are the disadvantages? Disadvantages is basically we have a noise. Okay, noise present in the basically we have low signal to noise ratio, and we have a low spatial resolution of this EEG signals. Okay. So now we will come to the how we combine this EEG analysis using ML. So we know that ML, machine learning algorithms, there are two broad types, basically supervised and unsupervised. But now we have other types of learnings also, like reinforcement learning and the semi-supervised learning and so on. Okay, so in supervised learning, what happens? We perform the classification and the output is discrete. Okay, and we perform the regression and output is continuous. Okay, so in unsupervised learning, there are actually in unsupervised learning, output is also continuous. And the more general example of unsupervised learning is clustering operation and dimensionality reduction operation. Okay, the clustering algorithms, you can say that our k-means clustering, and dimensionality is basically the PCA, principal component analysis. Now this EEG signal, when we analyze, so there are multiple steps. So what are these steps? Basically, first few steps are pre-processing, like removal of noise. Okay, then we have feature extraction, means you extract the interested points, and then we have a feature selection, means about among the interested points, which is we should use for further processing for training, and then we have a testing. Okay, model training and model testing. Okay, so let's discuss the regression. So in linear regression, what happens? Let's say linear regression is there. So in linear regression, we use single variable for prediction, and output is continuous. Okay, and now what is multiple linear regression? In multiple linear regression, we use independent variables for prediction. Okay, we use the independent variables, means more than one variable is there. Okay, in linear regression also independent variable is there, but in multiple linear regression more than one variable is there. So that's why it is called multiple linear regression. And that is one regression also comes in classification technique that is called logistic regression. Okay, but this logistic regression we use for classification. Okay, that is means in logistic regression the output is basically the discrete. Okay, so generally people confuse is that logistic regression is yes. So I mentioned this so that you should remember the linear regression and multiple linear regression is of the one class, and logistic regression is associated with the classification task. Now let's see, there are some methods which these two methods means struct and raw. Okay, these two methods are there, and these two methods are proposed in 2017 and 18. They uses the logistic regression for analysis of EEG signal. So in method 1, actually this seizure probability in present. Seizure means some kind of means a problem or abnormal EEG signals are there, means detection of these actually we call as seizure in a seizure condition. So in struct method, they use the logistic regression. They obtain the data, collected the data set from 4,772 participants, and they reported the AUC of 0.819. Okay, so why, first of all, let me first discuss the motive behind discussion of all this thing, so that if somebody wants to work on these biomedical signal or EEG signal, so they should know actually what is the current scenario, current status is there. Okay, so that we can develop our own method or work research our publish our own work on this. So they reported the AUC of 0.819. So it is good, but there is still chances that we can improve this AUC. You know, AUC stands for area under the ROC. Okay, so there is another method that is proposed by Roy, and in this method actually the target task is to automatic abnormal EEG detection. Okay, of course due to many reasons. Okay, okay, or we too much motion of the patient while capturing the EEG signals. So in this method they also use the logistic regression and the data associated with abnormal that 3.47% better performance. Actually in method 2 they also uses the RNN or this they report logistic regression, and we will see how SVM is applied for analysis of EEG signals. So SVM is basically supervised learning algorithm, and it is most widely used for classification, and now we have the support vector regression also, so we can use this for regression tasks. Okay, so actually what happens in SVM, SVM maps that training points so that classes are separated by maximum possible margin. Okay, classes are separated by maximum possible margin. So let's say we have two classes, so we have to perform the separation of these two classes such that the maximum margin should be present. Okay, so there are some optimization problems associated with that. So means and then we have a, and this is for the, let's say up to 0.2 we consider that okay, the data is linearly separated. Now, what is the case when data is not linearly separable? So in that case, when non-linearly separable data is there, so we use the kernel tricks. Okay, so kernel tricks basically means like Gaussian kernel, or when we go in more detail on SVM, you will find that the response or the decisions associated with SVM is highly related to the product of the training samples. Okay, so these things are there. So another training sample like SVM and models used for easy analysis. We are actually, let me just check any issue is there or not. Some messages are coming. That's let me just cross check. Okay, that's I think fine. Everything is fine now. Yes. Can anybody acknowledge? Means all these things, audio, video. Okay, I think everything is fine. Okay, so now we have a SVM. With the method one is basically proposed by Sai, and method two is by Hosseini. And in first method, the EEG artifact removal technique was present. Okay, means actually the artifact removal means we have signals with artifacts and without artifacts, and we used SVM for that classification. Okay, and the reported accuracy is 99.1. Okay, in method two, we use the EEG signals for facial expression detection. Okay, you see what are the means in different applications you can use this as you can use the EEG signal. So they use the 14. They have the 14 patients associated in this work, and the accuracy they have reported is 82.75 for detecting the different types of facial expressions. Okay, that is. Okay, now next is k-nearest neighbor. K-nearest neighbor again is a supervised learning algorithm. It is widely used for classification. Now it is also we can use for regression also. Okay, and we actually in this k-nearest neighbor, because nearest is word is there, so it is somehow related to some kind of distance. So in distance function basically is a major role for execution of the k-nearest neighbor algorithm. Okay, so now next is artificial neural network. So in neural networks, shortly abbreviated as NN, or artificial neural network abbreviated as ANN. So ANN is basically is is a mathematical model similar to human brain's neural networks. Okay, so in ANN we have a feed-forward neural network. So in this case the information flows forward and back propagation. Okay, so in neural feed-forward neural network we have information flow forward as well as backward direction. Okay, so we generally call it forward propagation and back propagation. Now why forward propagation? Forward propagation is basically used for prediction time when we are predicting something. Okay, at the prediction time we are actually use the forward propagation, and the back propagation we use when we are adjusting the weights to minimize the loss. Okay, we are adjusting the weights to minimize loss. And we have actually the radial basis function network. Okay, so generally people confuses with this. So it is actually a ANN, artificial neural network, with the use of activation functions. Okay, that is actually nothing but the radial basis function. It is a ANN, artificial neural network, with use of activation functions. Okay. So let's see some of the methods which used for EEG analysis using ANN, that is SINE in 2018, and SINE uses this artificial neural network for epilepsy classification. Okay, classes are there. So means classes are there associated with normal and epilepsy, EEG epilepsy cases, and we are performing the classification. So 100 samples are there. So, and they reported the accuracy of 99.3. Okay. So you can see it means how much work has been carried out in using ML for EEG analysis, specifically for epilepsy classification. And actually this next method is Cherry et al. Means in 2018. So they uses this artificial neural network for hybrid EEG analysis. So hybrid EEG analysis, basically it means they develop this method for a brain computer interface, BCI, and they uses the two methods. One is the EEG signal and another is called FNIST approach for capturing the brain signals. Okay, FNIST. So they use this FNIST signals as well as EEG signals for an analysis of the for improvement of the BCI performance. BCI means brain computer interface performance. Okay, so they reported the accuracy is about 99.3 when they uses this hybrid signals. Okay, so this is one of the another possible direction where instead of using simple EEG, you combine this EEG with some other type of signals also, and let's see what the performance is. Okay. So next is basically naive-Bayes. Naive-Bayes classifier is we all means is basically widely used for text categorization. So in test categorization, we use it is naive-Bayes is basically based on Bayes theorem, and it is very popular for like spam or spam mail detection or like that. In these. So in this case, in naive-Bayes, one of the very important property is that it considers the feature vectors as independent, even if the the feature vectors are correlated, but it assumes that they are independent. Okay. So okay. In actually, we have to the typical amplitude range of EEG signals is around is maximum it goes means in microvolt. So it is in microvolt range. So it generally there may be minor. It is very difficult to say, man. It is related to this specific band or this specific amplitude like that. Okay, but generally we have the higher amplitude. I mean, so in case of in case of the problem, epileptic problem, generally the change is high. Okay. So advantage is naive-Bayes. We have a in naive-Bayes case, the actually another advantage is that we can obtain the good performance when we have a smaller data set, even if we have a smaller data set, right? So let's say there are some methods which used for naive-Bayes model for EEG analysis. So one method is proposed by Sarmila in 2018. So it is again, it is detection of epileptic season. Okay, so they actually not reported the dataset information and they reported the accuracy of 100%. Okay, so some like this works are already done, you know, recently. So another method is Mumtaz, which actually uses this type-based algorithm for major depressive disorder classification. You know, means analyzing the depression using the EEG analysis. Okay, so they collected the very small data sets are there, means 30 uh, normal persons and 30 patients. Okay, they collected the data set using these total 60 persons, and they reported the accuracy of 93.6. So there if this data set is available online, let's say for example, through official permission, if we can use that. So if you obtain the accuracy better than this, and we also need to check in 2022-21, is there any method for the major depressive disorder? Okay, what are the reported accuracies there? Okay, so we can develop our own method for for better result, for better accuracy. Okay, so next is the decision tree, use of decision tree and random forest. So let's discuss more a little bit about it. So decision trees basically is related to asking questions. It asks questions to for the item to classify it. Okay, it asks questions, and based on these responses, it classifies the data. So basically, we have each question as a node, and we have a child node. Okay, and child node, it basically each answer of the question. Okay, let's say if I ask question, uh, any question which is in yes or no, answer is in yes or no format. Okay, so there will be child node, which will be the yes, one for yes child, one node, and no for another child. Okay, so based on that, you can make a hierarchy or tree also. Okay, you ask one question, there is a response. Let's say response is yes. You then ask another questions where the then response is, let's say no. Then you ask another question. Okay, so you can say that this yes no yes no yes no kind of tree will form. Okay, so that is actually the very popular binary tree. Okay, where each questions having the answer in the form of yes or no. Okay, so yes and no, basically these are the child node, and each parent node is basically a question. Okay, so let's discuss this decision tree and random forest. Okay, these are also for these are also supervised learning. Okay, so first of all, let's clarify that what is actually the random forest is the combinations of the decision trees. Okay, as name suggests, forest means is a collection, means something bigger. Okay, so we have a means 100 or 500 decision trees to form a random forest. Okay, this number is just an example, but you can change this number also. Okay, how much decision trees you want to form a forest, right? So the first method is, let's in 2018 it was proposed by Hugh, and it basically used for capturing the EEG signal for the analysis of driver fatigue detection. Okay, generally we go for drive from one city to another city, so there is a common issue that fatigue is problem is there. Okay, so they uses this decision tree, and they reported, actually when I say, see, when I say in method 1 they use decision tree, it does not mean they only use the decision tree. Okay, so they use some other ML algorithms also, and they reported that the performance of decision tree is better as compared to other used. Okay, that's why I only mention the which one is giving the best result basically. Okay, so we have a 22 subjects for forming the data set, and the accuracy they reported is about 94%. Okay, so we can still work on that. Okay, my idea is for giving this presentation so that if somebody wants to work in this area, so when how I encourage him or her to start working on that. Okay, means for simplicity, let's say I want to work in this driver fatigue detection. So what I will do, I will just go for this paper and see, and I will also see the latest papers. Okay, still in 2018, that is not very it's old paper. It is still considered a recent one. So you read this paper, do the state of the art work, and just see what we can do, or I can do, or our research group can do to obtain better accuracy, okay, or develop any new method like that. Okay, that is my motive, so that I can encourage all of you to, if you want to work in this, okay, how we can start working, right? So we have an accuracy of around 94%. So this is the 94% reported accuracy. So we can still improve this accuracy, right? So next is basically the method 2, which is Bose method. So in Bose method that proposed in 2017, it is basically the CZ detection, means abnormality present in the EEG signal. Okay, so they uses the random forest algorithm. The data set is associated with only 5 patients, and they reported the accuracy of 98%. Okay, so these are the general recent methods for this driver fatigue detection and CZ detection, right? So let's say we have an ensemble learning. So people also uses the ensemble learning for EEG analysis. So ensemble learning, we have actually the supervised learning, and we have the ensemble is basically the supervised learning, and ensemble, what we do actually, we combine different algorithms to improve the predictive performance. Okay, combining decisions obtained from different models. Okay, combining decisions obtained from different models, which will be used by our final model, which is basically the combination of different models. Okay, that is actually the ensemble learning. So that's this actually table 6 is for K means ensemble learning, not for K means. So method 1 is basically L et al. In 2018. They actually uses the age EEG signals for age prediction from brain signals. Okay, that is actually the age, predicting the age basically. Okay, so they use the this ensemble learning. And remember, if you recall, we are predicting the continuous quantity basically. You know? So that's why now this is not a classification problem. This is a regression problem. So they use this ensemble learning for a regression. Okay, regression task, and they reported the root mean square error of 8.46. Okay, means if somebody wants, if somebody obtains some other method, let's say uses some other method and receive the RMSE of, let's say the RMSE should be lower. So let's say they receive the ROC of 5.5. So the work can be published. Okay, and then we have this in data. They use 468 healthy and 297 patients. Okay, so now we have method 2. This is EEG classification. Actually, this EEG classification is seizure classification. You know, seizure classification. So they uses the ensemble learning. Now you see, method 1 is for regression. Method 2, ensemble learning, is for classification. So they uses the collected the patient data set from 8 patients, and the accuracy they reported is 97%. Okay, so now we have let's discuss some other methods. We have a LDA, that is called linear discriminant analysis. Okay, so actually this LDA uh, is basically the dimensionality reduction technique. Okay, actually what we do in this LDA, we reduce the dimensionality of the feature vectors. Okay, so while performing this LDA what it does is also separation between the actually the bit it enhances the between class variance, it increases the between class variance and lower the within class variance while performing that LDA. Okay, LDA motivates the interclass variance to be increased and within class variance to be decreased. Okay, so now there is one more term that is called principal component analysis. You must have heard. So what is the difference between LDA and PCA? See, let's discuss this difference in terms of dimensionality reduction only. So let's say we have a two-dimensional set of feature vectors. Okay, and we want to reduce them into one-dimensional set of feature vectors. Okay, so if you reduce the dimension using LDA, so if you are, let's say, doing the classification problem, then LDA actually motivates after reduction, dimensionality reduction, the cat means the separation between these two classes should preserve. Like, okay, so but when we use the principal component analysis, after projection into lower dimensional space or in lower dimension, the separability is not guaranteed. Okay, the PCA does not guarantee that after projection into lower dimension space, you will get these separable data. Okay, when I say separable data means separable classes. Basically, classes are well separable. Okay, but LDA somehow motivates that the after projection the separation should be there. Okay, so that is actually the one of the key difference between LDA and PCA projections. So let's say we actually use this LDA for dimensionality reduction. So these two methods, Kira and Yuan, they uses the one is for easy classification, one is for seizure detection. They use this LDA for dimensionality reduction only. Okay, so that's why this anything accuracy or like this accuracy or AUC values are not reported, because they only reduces the dimensions of the signals. Right. So now come to k-means clustering. K-means. So K-means is basically the unsupervised learning algorithm. Okay, and it is basically used for performing the clustering operation. So what it mean idea is that it minimizes the error between a cluster mean and points inside that cluster. Okay, means minimize the error between the empirical cluster mean. Okay, mainly basically, and the points inside that cluster. So in general, if we have a k clusters, we call that k means minimize the total. Okay, that k basically, why this k is there, that is the mean. So let's see what are the clustering algorithms. See, we have to perform the clustering and then we have to perform the classification. Okay, so the first method is OZDEM in 2017 is basically they use the EEG signals for emotion recognition. Okay, you collect the EEG signals from different emotions. Okay, and then first of all you use the k-means for forming the clusters. Okay, and then use the SVM for classification. Okay, so they use the 32 healthy subjects for creating the data set, and the accuracy they reported is 72.92. So in this area, this is one of the very means I think we can go in this direction on possible direction, because the result is good, but can be a chance, there is some chance that we can improve this result. Okay, then method 2 is Manjusha in 2016, which is used for epilepsy classification. Now they use it, first of all, instead of assuming that supervised classification, they consider the problem as a scratch. No? So means they first of all develop the k-means for forming the clusters associated with epileptic signals and the non-epileptic signals, and then you use the KNN algorithm for the classification. Okay, so 20 patients are there in their study, and the accuracy they reported is 93.0. Okay, so instead, now the motivation for this clustering is that, so let's say we don't have the supervised data. Okay, so we should not demotivate from that. We should use any clustering method. Okay, k-means clustering or any other clustering method. You make the data, okay, and make the clusters, and then you perform the this uh, any supervised classification. Generally, when we go in industry or somewhere, it is very difficult that for a particular application we will get a supervised data. Okay, so for any new application, always there is some chances that we will get a we'll have to do unsupervised. Okay, so that is one of the motivations. So don't get demotivated whenever you don't have the data also for the supervised. Okay, so let's discuss some of the conclusions. So we have the EG signal. We discussed the EG signal. What are the EG signals, and what are the different frequency bands and applications in ML? Okay, machine learning. So one thing I just want to mention, because I worked in industry also. So generally, most of the means researchers newly now, which those are new to this area, they think that let's say any epilepsy classification is there. So they think that we use the recent deep learning technique, a very deep network like this, so to get the optimal performance like that. Okay, but that is good up to some point. Okay, so see why I'm saying this, because when you are in industry, there may be some industry will have a very big budget for implementing the projects, or some startups or some industry may have the lower budget. Okay, so it is not always necessary that you will use the bigger neural network or bigger or deep learning methods for implementing executing the task. Okay, if you are able to, let's say for any task, let's say for epilepsy classification, I'm work, let's say I'm working, I means somebody works in any industry. Okay, so they have a limited budget and they reported the accuracy, let's say, of 97. And let's say, and another, using the, if we have the higher resources, so we can use the deep networks. So the deep networks are basically, yes, actually, people are going for this direction also. Means electronic system implementation associated with that. Yeah. So electronic system associated with that. Like designing of differential amplifier or like this, all these things. Electronic circuitry for making the model of the EG signal production. Okay, means there's some kind of electronic model of the same. Okay, people are doing this work. So what I'm discussing, so let's say we use this ML and we obtain the 97% performance. and somebody uses the let's say DN, for they reported the 98% performance. Okay, so it is not always necessary that when we have a limited budget we can go for ML, okay, which gives 97, and we can again test the methods or improve the methods so that we can get more than 97 or close to 98 or more than 90. Okay, so it is not always there. It is necessary that we should go for deep models or advanced models for the design of the hardware. Okay, for research purpose you can go. There is no any constraint. Okay, but in industries, if you go and work, you will find that uh, there is a budget limitation in some of the industries will be there, right? So we have a future direction, some of the future directions, and recently developed deep learning techniques for EEG analysis. Okay, now if you want to develop, you can use this technique for EEG analysis. And the one more very interesting technique is to use of EEG, use of your brain EEG signal to control the robotic arm or robotic object. Okay, this is actually the one of the very interesting area to work. Okay, and then we have a future is basically let's say this is one of the possible research direction. So we use this curvelet and sharelet for 2D objects or 3D objects. Okay, can we make the 1D version of these and use this for EEG analysis? Okay, these curvelet and sharelet are basically used for image analysis. So can we use this for convert these systems into for 1D and use this for EEG analysis? Okay, so these are some of the possible future directions. So these are some of the references. Okay, so whenever thank you, and whenever you want to go for any, or means let's say I want to do research on this, so you should do some sufficient state of the art work, means at least 5-6 months you should give for that for state of the art, then you will actually you will do very good work on that area. Okay, so thank you. That's all from my side. So should I stop sharing?
Thank you, sir. Now you can stop sharing. Sir, there are a few queries.
Yes.
One is from Anurag Verma. Which algorithm are good for hardware implementation for FPGA and microcontrollers?
See, means for hardware, see all the algorithms are basically are means it means applicable for hardware. There is it is not like that any, let's say, KNN is simple to implement or some other algorithm simple to implement. You can use any algorithm, because that's just a programming, and after this programming you have to do the corresponding hardware implementation. So it is not very related that let's say KNN is very simple to implement in hardware. Okay, so we first have to check the which algorithm is doing the best, and then you will go for hardware representation.
Sir, there is one more query from Vijay Khare. How to collect EEG data in case of decision tree?
See, means data is already there. Data is already there. You collect the EEG signals, and you form the feature vectors from them. Okay, decision tree is just an algorithm, it is not related to uh, cap EEG signal. Just see, first of all, we have the EEG signals, then you can use these different algorithms. Okay, algorithms are independent to EEG signals basically. Capturing EEG is different thing, and applying ML or decision tree on EEG is different thing. Okay, so you can use, there is no issue, but these two things are different. Don't consider these as same. Let's see.
And continuation to the same question, there is how to take yes and no in case of EEG signal.
Let's see, yes or no, I actually mentioned for the simple understanding of the this understanding of the decision tree. Okay, but in actual case, you have to, instead of forming the binary tree, you have to maybe form the some more complicated tree, non-binary tree also. Okay, this yes or no I just mentioned for the so that you can understand what is the typical decision tree. That is. I can check the, I think I should check the chat also. I think they are questioning in chat.
Yes, sir.
Yes or no, sir, can you please provide some easy data set in CFP? If Bhaskar, it is, I will see, my email ID will be provided by you, by the organizers. So you contact me. My email ID is basically amitv@IITDMJ.ac.in. So you can mail me, I will provide. Or if there is open source, any available, their availability is there, you can use that also. See, when actually in this discussion, I use the means general applications, general applications, so that when we discuss any one particular application, so the knowledge scope is very limited, so that's why I mentioned the general applicative brain emotion recognition, or like these different applications, so that if you want to go specifically on one particular problem like epilepsy or facial recognition or emotion recognition, you have to go for research papers. Okay, so, and the collection, see, these extraction of the EEG signal, like question is montage of electrode will be considered for epilepsy. So it is related to some kind of medical part, means this is also related to some kind of medical experts or associated industry experts which design the EEG devices. So my talk is basically focused on work is focused on the analysis of EEG signals. Okay, that's. What technique can be used to classify single channel EEG data? So when you say EEG data means there may be variations should be there. Okay, when we say the classify of single channel EEG data, means is there a sufficient variation is there or not? Let's say you are classifying the epilepsy and normal patients, so you collect data from epileptic patients and you collect data from normal patients, and then you collect these two classes and then you perform the classification. Okay, that is. See, let's say one is artifacts is very common. That is, see, in general example, somebody is, let's say any patient is there or any human is there, he is going for giving his EEG data. So when he moves around too much, there are too much movements are there. Okay, and let's say wires are there, you disturb the wires from your movements, okay, too much, so it will create the noise and artifacts basically. Okay, these are basically very common. Okay, Even if we move our eye muscles too much, na, that will also affect the EEG. So general what happens for children's, when because they for children's, when we are capturing the EEG data for children, we generally show them some any video or cartoon so that their eye will not too much dip, means eye muscle movement should be lower. These, you know, so these are the more and more concepts are there, because it will be difficult to discuss all these things in just in 1 hour. So that's why I thought I should focus on this, you know. So but these other area concerns are there, you know? So any other question? Okay, so my if you want to work with me, what statistical analysis can we do? Statistical like means statistically means you can measure, means let's say you collected who form the classes, for example, and then you measure the this mean, variance, kurtosis, skewness associated with this, let's say for a normal patient EEG data and abnormal patient EEG data. And you can analyze these values also, what are the difference between, what are the mean for normal, what are the mean for abnormal cases, what are the variance, kurtosis, skewness are there. You can analyze these things, these parameters. My email ID is amitv@IITDMJ. And if you still want to, if you have any query or anything related to research work in this area, so you can contact me. I will definitely reply. You know, very soon. So let me just stop sharing.
Thank you, Amit sir.
Okay. I think my screen is still visible.
Yes, sir.
Okay, let me just. So should I leave the meeting?
Yes, sir. You can leave.
Okay. So thank you very much. Huh?
Thank you,
Thank
sir.
you all the participants and organizers for giving me this opportunity. Thank you very much.
Thank you. Uh, Now it is time for lecture number 17, machine learning in resource allocation in wireless network. It will be covered by Argadeep sir. Argadeep sir, I made you the presenter. Am I audible to you, sir?
Yes, am I audible to you?
Yes, sir. You're audible.
Okay. Good morning, everyone. I'll just share the slides. Yeah, so this is visible to everyone.
Yes, sir. It is visible.
Okay. So yesterday, I think yesterday and day before, we have talked about some reinforcement learning methods, and also their some hands-on on that, new learning, other related algorithms. So today we are going to talk about machine learning for resource allocation in wireless networks. So I have tried to make this talk as a continuation of my previous talks so that remains connected. And yesterday there were many queries about some of the advanced reinforcement learning algorithms. So in this talk, I will talk about some advanced RL algorithms which have been applied in the context of wireless networks. So to begin with, this is the brief outline of my talk. First, I will give an introduction, followed by a block diagram, and then I will discuss about some ML approaches, machine learning approaches, and their applications in 5G. And then I'll take a specific use case, which is RL algorithms for radio access technology selection in wireless networks. Okay. Okay. So to begin, in next generation wireless networks, we are going to see high data rate and also many various type of applications which will be coming up. So the user application diversity as well as the demand for data rate is also increasing as we moving towards next generations of wireless networks. So therefore, it may be in older generations of wireless networks provide solutions which are maybe it is good for a specific kind of scenarios. But since the number of scenarios or number of specific use cases are also increasing, one particular type of algorithm or may not work well, or one particular parameter set may not work well for every scenario. Therefore, it is necessary to for the wireless terminals and antennas and user equipments to be smart so that it can adapt according to the scenario. Therefore, as we know that there is something called quality of service. Okay, so for example, one quality of service example is for voice user, you need to maintain certain data rate. Okay, so for example, 20 kbps or 64 kbps, this kind of data rate is there according to different standards. So this is the example of quality of service, QoS. Okay, so to maintain these QoS guarantees that are applicable for different applications, we need some intelligent learning methods and decision making to assist the radio basically. So, so people envision future smart 5G terminals where they automatically select wireless resources, because there are many terminals and many more base stations that will be coming into picture. As you know, that in 5G there is something called millimeter wave. For millimeter wave, the range of the signals are very less compared to I mean, although they provide high data rate, the range is less. So it is expected that in a city or I mean, in a typical city, there will be hundreds of base stations. So therefore, controlling them together, running a centralized algorithm, or having some centralized control, or having some manual control is very difficult. So therefore, it is envisioned that future smart 5G terminals will have autonomous features driven by AI methods, and machine learning is going to play a very crucial role in automatic selection of wireless resources in 5G networks. So what are the typical areas where machine learning is going to find its application is cognitive radio, massive MIMO, device-to-device network, heterogeneous network, smart grid, energy harvesting, and whatnot. So in today's talk, I will pick one of these things, that is heterogeneous network. So a heterogeneous network is typically a network consisting of different type of access and different type of radio access technologies. So what are radio access technologies? For example, Wi-Fi. Wi-Fi is a radio access technology. 4G LTE is a radio access technology. CDMA is another. CDMA this is another radio access technology. 3G is another radio access technology. So, when the multiple radio access technologies are present together, call it a heterogeneous network. So, see later that how ML finds its application in a heterogeneous network setting. So, this is a block diagram of a typical future wireless system. Here, this is an antenna which is connected to a RF chain. Then the RF chain is connected to a ADC or DAC converter. And then based on the observation, the machine learning algorithms compute the utility. Okay, so this is the block basically which is the focus. Okay, so machine learning algorithms will compute the utility, and then using the utility, it will select a particular strategy, and then that strategy will go into this antenna. So what is happening is this antenna is now being controlled by the machine learning algorithms. Okay, so these machine learning algorithms, what they do, they compute some utility, based on the present observation, and then they refine their strategy on the fly. So this is the learning block. What happens? Observation comes, machine learning algorithm adapts itself, and then it computes the utility, and based on that it refines its strategy, and that strategy is fed back to the antenna. So that way the system evolves, and we get a better and better system. Okay. So, so as we see in the block diagram, the next generation networks need to learn the optimal system configuration autonomously. Okay. So intelligent radio functionalities involve spectrum access using learning, power control, adjustment of transmission protocol. So whenever, depending on the scenario, you adjust the transmission protocol. For example, you may have heard about different modulation techniques, right? This PSQ, PSK, BPSK, QAM, etc. So depending on the channel condition, this the modulation scheme also changes, and then how to do it autonomously and for a bigger network. But in today's network, you will see that this kind of algorithms are already there in a single base station, but these base stations operate independently. Okay. So it may happen that the decision chosen by one base station is going to impact the other one, okay, because there are some users which lies in the cell coverage, cell edge. Okay, so how to do that in a autonomous fashion? That's where machine learning is going to be instrumental. Okay, so this is a survey paper which is little old, but I feel this paper was written at a time when machine learning is started. Machine learning has just started penetrating the next generation wireless network. So this is a very good survey paper to look into what kind of techniques has been used in the past also, and in recent I mean in the past and present also. So any questions till that until this point? Okay, so so someone is saying my voice is not clear. It's uneven. It's so. Is it clear now? Hello. Okay. 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 So I'm getting. So Lakshmi, she's saying that kindly unmute me. Any specific questions she wants to ask?
Sir, good morning, sir. Sir,
Yes.
can you just open your last slide? I have a question to ask from that slide.
Sure. Yeah.
Sir, intelligent radio functionalities in that spectrum access using learning. So, what do we mean by that? Since I have worked on this, so I want to know what does that mean, spectrum access using learning.
So this can be one thing, can be this cognitive radio thing where there are like primary and secondary users, and then based on the availability of spectrum, it basically accesses the spectrum, right? There are
Okay.
different two kinds of, that is one thing. Second thing is, for example, in a setting where there are millimeter wave and LTE base stations, then there can be like so LTE operates in something around something less than 1 gigahertz or something, yeah, some 900 megahertz in this range, and then millimeter wave is typically I mean much higher frequencies. Okay,
Yeah,
so
yes.
yeah, so that is also some kind of spectrum access, that where you want to go based on the channel condition. So that can be one spectrum access issue. So yeah.
So, what do we mean by learning there? I mean, are we applying any, matlab, how do we apply machine learning there?
Yeah, you can apply learning in the sense that uh, this channel, every channel has a specific characteristics, right? You have heard
Yeah,
about
sir.
relay fading, this kind of
Mm.
stuff. But relay fading has a specific parameter,
Yes,
right?
sir.
So for
Yes, sir.
example, The LTE band might have some relay fitting with some parameter, but the other band has some other relay fitting with some different parameter. Now, when in a heterogeneous network kind of setting, when there are multiple spectrums in 5G, you will see that there are support for Wi-Fi as well. Okay, so there is something called non-3GPP interworking function. Okay,
Okay.
so that like supports non-3GPP accesses also like Wi-Fi. So when this kind of multiple spectrums are there, it is not possible to uh, estimate the channel condition or know the parameter for like every spectrum. So learning basically learns it rather than knowing the parameters offline. It learns it on the fly.
Oh, okay, okay, sir. Yeah. Thank you, sir.
Okay, so moving on to the next slide. These are ML approaches and their application in 5G. Okay, so as you have already heard about these techniques before, definitely supervised, unsupervised, and reinforcement machine learning approaches can be classified into these three categories. And this regression model, SVM, KNN, these kind of models are useful for supervised learning. This machine MIMO channel estimation, detection, and user location, behavior learning, classification. Okay, this kind of stuff is related to also wireless also. For example, when there is a video streaming going on, okay, so 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 for example, yeah, there is a video streaming going on. There is a live cricket match that is happening, and then live cricket match is being broadcast to people inside and in a particular area. So depending on the uh, type of users or their location, they may be classified into two categories: good users, bad users, or maybe more than two categories. And then if you can classify them in some algorithm, then it becomes easier for the base station who is transmitting the data to do specific multicast, 2 3 multicast it has to do, and then it can reach every user. So this kind of issues are very this kind of use cases find its application in machine learning based theory are useful in this use cases. Also, there is Bayesian learning where spectrum sensing in cognitive radio, Bayesian learning is useful. Among unsupervised learning techniques, K-means clustering, PCA, ICA, these are also finding its application in fields like headnet clustering, Wi-Fi association, D2D clustering, spectrum sensing, etc. Anyway, today we will talk about reinforcement learning techniques such as a Markov decision process, which I think I have already covered in last two lectures. Also, POMDP. Can someone guess what is POMDP based on Markov? So Markov, this is a variant of Markov decision process. So any guess what can be POMDP? Okay, so yeah, so POMDP is basically partially observable Markov decision process. As you have seen that in Markov decision process, there is something called state space, right? So POMDP is when partially observed, the states are partially observed, not fully observed. You do not know in which state you are. Okay, so then it is called partially observable Markov decision process. And also Q-learning, multi-arm bandit, all these learning techniques have been very useful in resource allocation under network condition, energy harvesting, spectrum sharing for D2D networks, and headnet user association. So I think the focus of today's talk will be a combination of this part and the last point, headnet user association. Okay, so yeah. So I will now go into the reinforcement learning algorithms for radio access technology selection in LTE Wi-Fi heterogeneous network. Okay, so there is a heterogeneous network where LTE and Wi-Fi, both these radio access technologies are present, and then you are trying to select and to associate users to one of these based on certain criteria. So, so that's how it will. This is the overview of the entire flow of algorithm that we are going to talk about today. you know that this optimal radio access technology selection. What is it? This is like there is a network. Okay, so there is a heterogeneous network and it has LTE base stations and it has Wi-Fi access point. Okay, so now in this network there are users arriving and departing in some fashion, some according to some randomness. Okay, for example, can map it to your real life scenario. Maybe you and your friend and many other friends in your locality are sitting in their respective homes or in a particular area, and there is a Wi-Fi access point, and there is a mobile tower, 4G tower, which is present there, and then you are making two types of calls. One is you are making voice call, and you are making data call. Data call means you are, for example, using WhatsApp or downloading some file or playing some movie in your mobile. Okay, so there are two kinds of call. One is you do voice call, another is data call. Okay, so now what kind of calls should be associated to what kind of network, right? So if it's a data call, should it go to Wi-Fi or LTE? If it is a voice call, should it go to LTE or Wi-Fi? Obviously, this is not a static decision because based on the number of users, the decision should change. Okay, so as you have so now when what happens is, for example, you want to maximize the total system throughput. Okay, so when you try to maximize the total system throughput, what happens is usually the voice calls get blocked. Why is that? This is because data calls has a higher throughput, right? You know that when you download a file, you see 2 Mbps, 3 Mbps, 4 Mbps, but when you make a voice call, the data rate is in kbps. So when you want to maximize the total throughput, it will what will happen is the voice calls will get blocked. That's why it is important to consider a constraint on the voice user blocking probability. So now what is my model? I want to, there is a network where there are LTE base stations and Wi-Fi access point, and then you are trying to associate users to these networks. Users are coming randomly and departing randomly, and you want to maximize the total system throughput. But maximization of total system throughput leads to blocking of voice users. Therefore, what you are doing is you are maximizing the total system throughput subject to a constraint on the blocking probability of voice users. So is that clear to everyone? What is the setting? Okay, I do not see any answer. Okay. I hope this is clear to everyone. Okay. So now there are traditional methods like value iteration algorithm. So since you know about MDP, constrained MDP is just an MDP with a constraint associated with it. Okay. So what is the constraint? Constraint is the blocking probability of voice user. So this is known as constrained MDP. Okay. So someone is saying you are not clearly audible. I don't know, my network is having some issue. Okay, I will try to keep my mic in front of my mouth so that you can probably hear better. I'll try to be loud also. Okay, so there is one question which is how to select between 2RAT CMDP. Yeah, I will come to that. This is a question by Esha. So I will come to that, how to select 2RAT using CMDP. So right now it's a constrained MDP problem. Okay, and constrained MDP problem. So you are already familiar with MDP, and this is a associated constraint. There is a single constraint associated with it. Okay, so now there are many techniques to solve this problem. One of them is known as value iteration algorithm. Okay, so value iteration algorithm has a course of modeling. So what is Karpov modeling? As you have seen before that it requires the knowledge of the transition probabilities between different states. If you remember, there was a term like this. There was a term like this: P S S dash A, right? So this is the transition probability between different states. This knowledge is required. So this is known as the model. So therefore, this knowledge might not be present every time in the network. Therefore, this technique suffers from the Karpov modeling. Okay. Now there are traditional algorithms to solve this, as Q-learning, as you have seen in the last lecture. Q-learning does not suffer from the Karpov modeling because it solves the problem without the knowledge of this. Okay. But what are the issues? As you already we have discussed that the issue is slow convergence and space computational space complexity is also high. Computational complexity is also high. So do you remember what was the space complexity of Q-learning algorithm? If the number of state is say S, can any of you answer in the chat if the number of state is S and the number of action is A, then yes. So I have got the answer. The space complexity is S cross A. Okay, so therefore the space complexity is very high and computational. Okay, so Manish has a question. I will come to that at the end of the talk. High space and computational complexity. So to address these two issues, what I am going to do. Okay, so now if I solve this problem as using Delben equation, which I have shown you last lecture, then what I get is a threshold structure. So basically it says that you behave like this till this end, and then from this point onwards you behave like this. Like from up to this point you select the best select, you associate the user and then you block. Okay, so that's the optimal action, optimal policy. Say up to this point you associate the user and then you block. Okay, so now is knowledge of threshold structure can be clubbed with a RL algorithm, then we can search only within the set of threshold policies, and the set of policies which are not threshold in nature, that can be discarded. So this gives rise to something called structure aware learning algorithm, because we are exploiting the structure, threshold structure within the RL setting. Okay, so what happens is that the convergence also become fast, the storage complexity and computational complexity both become lower. Why is that? Convergence becomes fast because my policy space is smaller. Previously it was set of all policies, now it is set of threshold policies. Therefore it finds the best policy quickly because it is searching within a smaller search space. Storage and computational complexity is also reduced. How that is done, we will come in upcoming slides. Okay, so yeah, so this is my system model. This is a 4G wireless base station, and this is a Wi-Fi access point, and these are users, and voice user can be only associated to the LTE base station, and data users can be associated to either LTE or Wi-Fi. So there is a Poisson arrival of voice and data users with mean lambda v and lambda d, and the service time is exponential with parameter mu v and mu d. Okay. So voice user can be served only using LTE, and data users can be served either LTE or Wi-Fi. Okay. So as we have already discussed, we are finding optimal association in LTE Wi-Fi network where we want to maximize the total system throughput and subject to a constraint on the voice user blocking probability. And also there can be a offload. So for example, one user is already associated to LTE, it can be offloaded to Wi-Fi. It can be moved from LTE to Wi-Fi. So there is a controller sitting somewhere here, it takes the decision. Okay, so voice user can only go to LTE, data user can go either way, and data user can also be offloaded from one network to another. Okay, this is the setting. Okay, so now this is a Markov chain IJK, where I is the number of voice user, J is the number of data user, and K is the number of data user in Wi-Fi. Okay, so this is my Markov chain, and whenever there is a voice user arrival or data user arrival or a departure, we need to choose a decision. Okay, so these are my constraints. The first constraint tells that the total number of resource block in LTE is C, and this means that total number of resource block is C. This is like the limitation. You cannot give more than C resource block to the users. and this is like the number of users in Wi-Fi for guaranteeing certain minimum throughput. Okay. So this is my state space. Okay. So state space is ijk, I is the number of voice users, j is the number of data users in LTE, and k is the number of data users in Wi-Fi. And whenever there is a data or voice user arrival or departure, I need to make a decision. Now, what are the decisions? Okay, there is a question. Okay, yeah, there is a Manish question. I'll come to that later. Okay, so what are the actions? Voice user arrival, it's accept in LTE or accept in LTE with data offload to Wi-Fi or block. Okay, so these are the actions available for voice user arrival. Either you can accept the voice user in LTE, you can accept the voice user in LTE and data user, one data user you can move to Wi-Fi, or you can block it. Similarly, for data user, you can either accept in LTE, accept in Wi-Fi, or block. And when there is a departure, you can do either do nothing or do a data offload to a RAT from where there is a departure. So this is my action space based on the event. Voice user arrival, 3 actions. Data user arrival, 3 actions. And then departure, 2 actions. Okay, this is my action space. And okay, sorry. Yeah. And what is the reward? Reward is the total system throughput under that state action pair. And this is the cost. Whenever there is a voice user blocking, cost is 1, else it is 0. Okay, so this is the reward and cost. So when the total system throughput is the reward, and cost is 1 when there is a blocking. Okay, so now what we want to do is we want to maximize the average reward. Okay, and subject to a constraint on the average cost. So this is the average reward, this is the average cost, and we have a constraint. So this is known as constraint MDP. If we remove this constraint, it will become a normal MDP. Okay. Now to solve this, first we have to do this thing which is known as the equivalent unconstrained MDP. So we subtract the cost from the reward and multiplying factor beta. And then I use a combination of value iteration algorithm and gradient descent on beta to find the optimal policy. And as we have known, since it requires the knowledge of the transition probabilities, it suffers from the curse of modeling. Okay. So so now we see that there has been a structure of the optimal policy. What is that? The structure is you follow certain action till this point and then follow some other action. So this is like a threshold structure. So similarly for data user also, up to certain threshold you serve them using Wi-Fi and then you serve them using LTE. Okay, so this is my structure, that up to certain point you choose action 2 or action 4, which is accepting, and action 1 is thereafter it is action 1, which is blocking. Okay, so this is known as threshold structure. So this proof and other stuff you can find in this paper. Okay. Okay, so this diagram, this slide actually you have shown before. I will just very quickly go through it. So this is like the Q-learning algorithm to solve this problem, but it suffers from slow convergence, high storage, and high computation complexity. So this algorithm you will find in this paper. Okay, so now I have talked about post-decision state yesterday. So now I will quickly show you, quickly give a like a brief overview of the post-decision state framework. Okay, what is happening? Are you familiar with this equation? Have you seen this before? Right? Yesterday you have seen this, something similar to this Bellman equation. Yesterday you had a discount factor gamma. Here today there is no discount factor because I am considering a average cost problem, not a discounted cost problem. But this equation is basically the Bellman equation. Now if I consider a state, okay, so remember the state is like ijk. Now I choose a decision and then there is some arrival or departure. Based on that it moves to some state I dash j dash k. Okay, so if I consider an imaginary state, which is known as the post decision state. Okay, so imaginary state is just after the decision but before the arrival or departure. So for example, its system is in state ijk. I am accepting one user. Okay, and then there is another user arrival. So the system will be I plus 1 jk. That is my post decision state. Okay, So IJK, from IJK, just after taking a decision, it goes to a imaginary state, which is known as the post-decision state. And then after that, based on the next action, you go to the, based on the arrival or departure, you go to the like the normal state. So this is the imaginary state. Now, if you instead of this S, if you write a Bellman equation for S dash, then what happens is that this thing, this summation comes out. Why is that? Because previously, what was happening is that you first get a reward, and then based on the transition probability, you go to certain state. But now what is happening is that you are in state this, first the event happens, and then you, based on the event, you go to some next state and next PDS. So therefore, event comes in the beginning, event comes first, and then you get the reward. So therefore, this thing comes out. Now this has a very good interpretation, because since this is coming out, I can directly work with S directly work with S test, I mean value function. We did not go to Q function. Earlier we had to work with Q function because this was inside. So therefore, uh, since this is inside, if I do averaging, I cannot get this because this is inside max operation. This is not linear. Now it has become linear because this is outside. So now I can directly work with this, and that's the basic idea. I mean, scheme is something similar to Q learning, but now since we are working with the state value function, therefore the storage and the computational storage complexity basically reduces, because you do not need Q function at all. So you can directly work with value function. Okay, so any questions for this till this? So I'll just recap again. Previously, we had a Bellman equation where the transition probabilities are inside, because first you get a reward based on your action and then the transition happens. But now if you are considering an imaginary state where the state is just after a decision, then the event happens first, and then then it goes to the next state. So therefore, this summation is basically outside now. It is not inside. Okay, so therefore, now since it is outside, this can be replaced using averaging. Previously, since it was the inside, so it created a problem. That's why you need a Q function, so that now when you write in terms of Q function, then you don't have max over A, so it becomes linear. Okay, but here it is already linear because summation is outside. So therefore, you can write the scheme without. I mean, you can replace this averaging by averaging over time. So you can directly work with the state function. We can directly work with value function of the state rather than working with Q functions. Okay, it might seem little complicated in the beginning, but I mean, there is a nice reference for that which I already shared yesterday. You can look that to find what is this post-decision state framework. Okay, since there is no question, I'll just move. Okay, so this can be now replaced by averaging over time. So this is my PDS learning algorithm. So now, as you see, this is looks similar to Q function, Q learning, but where you have this 1 over 1 minus G weightage on the value function, and then G weightage on the currently learned reward. Okay, so it is similar to this, and this is some gradient descent on the Lagrange multiplier. So there is something called time scale, which I am not going in detail into it. It basically, this G and H are separated. G is like a faster time scale and H is like a slower time scale. It's like you are changing V rapidly and changing beta slowly, or in other words, equivalently, the Gn and Hn has some properties. which needs to be satisfied, and this is my post decision state learning algorithm, which looks similar to Q learning, but instead of Q function, you have value functions directly. Okay, so now I will go to the second algorithm, which is the structure aware learning algorithm. So the key idea is we want to get rid of the computational complexity. Computational complexity is very high. Okay, so from where, okay, again, not audible.
Sir, you are audible. Sina, you need to check your system. There may be some issue.
Okay, so the key idea is reducing the computational complexity, and so the fix a policy. Okay, just a second. So the key idea is we want to reduce the computational complexity, and by getting rid of the maximization operation. Okay, so what do you want to do is we want to fix a policy for a given threshold vector, because threshold basically says that okay, up to this threshold you want to you perform this action, and after this threshold you perform another action. Okay, so first what you want to do is you want to fix a policy for a given threshold vector, evaluate it, and then compute the gradient of the average reward with respect to that threshold vector. Okay, and then update the threshold vector in the direction of the gradient. So what is happening now is previously there were computationally complex because you had to perform maximization over A operations. Okay, the number of actions are A. So what you do is now since we know that the optimal policy is has a threshold structure, so I am searching only within the set of threshold policy. Okay, so what I do, I find a given threshold vector. Given threshold vector, I know that up to this threshold my action is accepting, and then it is blocking. So for a given threshold vector, I evaluate how good my policy is. Then I perform a gradient operation. The gradient basically shows that in which direction you want to go. Okay, so after computing the gradient, you update your threshold vector in that direction. Okay, so it's a gradient based approach. You are updating the threshold value based on the gradient of the performance measure, which is my average reward. So this is the formula for computation of gradient. Okay, so this is like the stationary probability of state S, and this is the gradient of reward, and this is the gradient of the transition probability. Okay, this is the value function of the destination state. Okay. So we evaluate a fixed policy for a given threshold vector, and then compute the gradient of the reward using this formula. I compute the gradient. Remember, this PSS theta is not known to me. Okay, so so we fixed a policy for a given threshold vector. We compute a gradient of the average reward with respect to this threshold vector, and then we update the threshold vector in this direction. So there are two parts. One is policy gradient, finding the gradient of the current policy, and then policy improvement. This is nothing but a gradient descent algorithm. So first I do a gradient of the policy and then improve my policy in the direction of the gradient. Okay, and yeah, now we have to find the compute the gradient of the transition probability. So what I'm going to do. So so what is happening is now my policy looks like this. Okay, so it's like a step function, but it is defined at discrete points, because up to this point the policy is like accept, and then after that it is block. Okay, now what I want to do is I want to perform this gradient operation. Okay, but it is not possible because the theta, I mean the policy itself is defined at discrete points. We want to find this operation, but we want to do this operation, but the policy is defined at discrete points. Therefore, I need a continuous approximation of the policy. Okay, so this policy is discrete. I approximate it using a sigmoid function. Okay, this is known as sigmoid function. Okay, so this is my approximation. The equation at the bottom. This is my approximation, and now I will be able to take a derivative of this. Okay, so now if I take a derivative of this term, what will happen is this del fs theta will come here, and here I will get a del fs del minus del fs theta, and there will be p1 minus p0 by p1 plus p0. Okay, so yeah, so that's what I will get. Okay, so now you will see that if I take a gradient, the multiplying factor for p0 p1 is same, del fs theta, but the sign is opposite. Okay, So that means I choose P1 and P0 with equal probability. What is P1? P1 is my blocking and P0 is accepted. Okay, I choose them with equal probability. So this is the resulting equation. I am not going detail. Okay, so this is the thing. This is the gradient of the transition probability, and I choose P1 and P0 with equal probabilities, and then there is a minus negative sign before P0. Okay, so I just toss a coin. If I get head, I accept the user. If I get tail, I reject the user, and then if I accept, I multiplying factor is del fs theta. If I reject, the multiplying factor is del fs theta with a negative sign, and then this is my update. This alpha n and beta mu n are like this random variable for head and tail. Okay, so yeah, this may look complicated, but the intuition is basically you are doing a gradient operation, and this whole term is driven by this equation. Okay, so with half probability you are choosing P0, with half probability you are choosing P1. So that is being captured by this -1 to the power alpha n, and this is coming because we are having this term. And after multiplying del PSS theta, we are multiplying this VS dash theta. Therefore we are getting this term. Okay, so we choose. So this is my learning algorithm now. If you see this scheme, this is the iterations. Okay, if you see now there is no maximization operation, like the max over a is vanished. Okay, so max over a is vanished now. So you see the computational complexity is greatly reduced because there is no maximization operation. So the flowchart is similar. You determine the event, you choose the action governed by the current value of threshold, and then you update the value function in the faster time scale and update the value of theta in the slower time scale, and so on. So this is how the structure of our learning algorithm works. Okay. So, what are the advantages? Advantages is now we have reduced computational complexity because there is no maximization operation. So the number of computation is order of 1 instead of order of a, which was previously. Storage complexity is reduced because since this is a storage threshold policy, the part where you are blocking, right, those states will not be visited because you are blocking there. So you need to store smaller number of states, and the convergence is also faster because we have a okay. So one is Viranjan is asking what is order of a. A is the size of the action space. Okay, so this is my order of a. So this is me. So basically, previously in Q learning, if you go to Q learning, in Q learning, if you remember, uh, this was the equation, right? There was a max over a, but now in this equation, there is nothing like that. There is no max over a here. So it's a order of 1 computation. Only 1 computation you have to do. So it's like a great reduction in the computation. Okay, storage complexity is set of threshold policies are only there, so therefore some of the states are not visited, so we need to store smaller number of states, and the convergence is also faster because we have a smaller policy, the set of threshold policies. Okay, so there is another question that why such reduction? Such reduction happens because you are dealing with threshold policies only. So threshold policy is what? Threshold policy is determined exactly at particular point. If you know the value of threshold, you know which action is there in different states. And the threshold value you have to learn. Previously, you are learning the optimal action in every state. Okay. Now what you are learning is only a threshold value. If you know the threshold value, you know up to this threshold, my action is this. After this threshold, my action is this. So for a given value of threshold, there is no order of a computation because if you know the value of threshold, you know the policy completely. Therefore, there is that's why there is a reduction because now you are not you need not find best action in every state. You need to only find the best value. Okay. So therefore, you need not have order of a computation. Only order of one computation is sufficient. Convergence is also faster because we are dealing with a smaller policy space, set of threshold policies only, and it is applicable to any general problem. So later, binary thresholding is hard thresholding. Yes, binary thresholding is hard thresholding. Viranjan is asking this question. But if you see, if you go to this this diagram, okay, you see that the hard thresholding I am approximating using a soft thresholding. So what does this sigmoid curve mean is basically in every point you are choosing policy P1 with probability Fs theta and P0 with probability 1 minus Fs theta. So at any point, it's like with some probability you are blocking, with some probability you are accepting. So this hard thresholding is now made a soft thresholding using approximation. But in reality, the hard thresholding is the best policy. Okay, so that you can that you can show using some using, if you solve the Bellman equation, you will see that the hard thresholding is the best strategy. Okay, so does it answer your question, Aviranjan? How should I come to know from which algorithm suggest I'm learning? I'll come to that. Okay, so now I'll show some simulation results. Okay, so this is the storage complexity of Q learning, order of state space time, order of cardinality of state space time, cardinality of action space, and computational complexity is order of A. PDS learning, it reduces to order of state space, which is C square W, because why it is C square W? Because if you have to go back to this curve. Okay, so I plus j is less than equal to C, as you have seen before. Yeah, so this is the term, right? I plus j is less than equal to C, and k is less than equal to W. So this triangle is basically I plus j is less than equal to C. Okay, so what is the area of the triangle? I mean, basically, right? So from here I get C square, worst case, and then this is W, this is W. So multiply. So W can be at max, k can be at max W, and I plus j is less than equal to C. Using that, I get C square W. Okay, so now see how much computation you are reducing. The PDS learning, the computation is order of C square W, and in the structure you are learning, it even reduces. It's like C square plus CW, which is even smaller than C square W. And computational complexity, Q learning was order of A, post decision state learning is order of A, structural learning is order of 1. So computation, storage, and convergence is here. Okay, this is convergence. You see that the blue one is the structure error, which is converging very fast. It's like almost converging at the convergence means basically it does not change much. It converges. So it is converging very fast, around say 100 to 100 iterations. Whereas Q learning, it's converging at this point, like more than 2000 iterations. So this structure error learning is a big advantage compared to Q learning in terms of storage complexity, computational complexity, as well as number of iterations. Okay, and some more simulation results. Voice user data arrival rate. We see that the performance is like throughput is also like quite better than the on-the-spot offloading. Oh, so on-the-spot offloading is what is happening in today's mobiles. Okay, in today's mobiles, if you see that when you go to Wi-Fi, whenever there is Wi-Fi, it connects to Wi-Fi, right? And whenever there is no Wi-Fi, it will connect to 4G. So this is known as on the spot. Okay. So basically, this algorithm is performing better than the algorithm implemented in today's smartphone because the throughput is much better. On the spot is here, somewhere here. Okay. So this algorithm is performing better than the algorithm implemented in today's smartphones. Also, it is converging very fast compared to other algorithms. So to conclude, we have considered an optimal rat selection problem where we maximize the throughput subject to blocking probability constraint. We have proposed learning algorithms which exploits the threshold structure, and it takes a gradient based approach for the update of threshold iterates. Also, we have lesser storage computational complexity. Convergence is also faster, and later we have generalized this approach to any problem. So it need not be from wireless networks. You can apply it to any problem where threshold structure is present. Okay. So details of the algorithm can be found in this paper, and the last paper is basically talk about the generalization. In the last paper you will find, this is also published now, so you can find the last generalization of the algorithm in the last paper. Okay, so some future directions. Other areas of resource allocation using ML are power control, scheduling, spectrum allocation. You may have heard about scheduling techniques like proportional fair, which tries to maximize the log utility, and then it was then round robin maximum CQI. So there has been work how these things can be made better or made automated using machine learning, and also there are work in transfer learning, imitation learning, federated learning, and so on. So these two papers will serve as a very good reference if you want to know about this stuff. And I believe deep learning is also going to play a very crucial role. So these references will be a good reference to find these areas. Okay, so thank you. I will now take questions. Okay, so Manish was asking one question, that is, how should I come to know which algorithm is more suitable for spectrum sensing? So I would request Manish to go to this. So I will share the slides later. So you go to this reference, the first one. Yeah, this one. Okay. So this reference will be a good reference for finding out which kind of algorithms are being used for spectrum sensing, and then based on your application you can choose which is better, because it depends on the problem. You cannot say that one is better than the other. It really depends on the type of problem you are handling. Okay. Another question. Yes. Okay. Okay. So any other question, you can unmute and ask the question, or you can post in chat also. So there is one question. Can we, from Rajesh, can we use ML for wireless relay network? Again, I'm saying that unless I know the problem completely, I cannot say whether ML will be useful. So I would suggest that since you are interested in doing that, you just search internet that how wireless relay networks, what are the ML applications that has happened. Okay, so you have a survey of that, and then you will understand better. Unless I know the problem particularly, I cannot say whether ML will be useful there. But definitely, nowadays I think it is being used for wireless relay networks also. For example, there is something called this IAB, right? Integrated access and backhaul, where I think this relay is useful. Integrated access and backhaul. So where there is this concept of relay, which is very relevant in today's 5G standardization. So you can probably refer to those papers also. Yeah, Omol is saying to share the slides that I will share with the organizers. Okay, so yeah, I have answered Rajesh's questions already. Yeah, anything else?
Lakshmi, you are unmuted. You can raise your query.
Yes, please go ahead.
Participants, you can raise your hand to ask queries. Argadip sir, there are no queries in the chat box also.
Okay. Okay, so if there is no queries, then yeah, thank you everyone. And okay, so there is another session tomorrow for this some hands-on on this topic also. So we'll meet then. Okay, thank you very much. So maybe may I leave now? So
Yes, sir. Thank you, Argadip sir. We will again meet tomorrow at 1:30 p.m. for the hands-on session.
Thank
you. Now it is time for lecture number 18. Machine learning in energy efficient communication. It will be covered by Dr. Rakesh Kumar Jha from IIT DM Jabalpur. Before we start the session, we would like to share his brief profile. Dr. Rakesh Jha sir is Associate Professor in Department of Electronics and Communication Engineering at Indian Institute of Information Technology Design Manufacturing, Jabalpur. He is author of most popular articles in the area of 5G networks. Dr. Rakesh Jha's proposal related to the router configuration of wireless communication has been accepted by International Telecommunication Union in 2010. He has received the Youngest Scientist Author Award by ITU in December 2010 for the same work, and he has also received a PAN fellowship. He has been listed the top 2% of researchers or scientists in the world in telecommunication and networking and engineering field. He has filed 7 patents, out of which 4 have been published. He has more than 4,001 citations in his credit in the area of wireless communication. Welcome, Rajesh, sir.
Yeah, thank you. Thank you.
Sir, you are connected with 2 systems. I think.
Just.
Okay, sir. No issues.
I'm audible?
Yes, sir. Yes, sir,
yeah.
you're audible.
That system was backup because sometimes your light fluctuation. No,
okay, sir.
Yeah.
Sir, now I'm making you the presenter.
Yeah.
Sir, welcome to this program.
Yeah, thank you. Is my slide is visible?
Yes, sir, it is visible.
Yeah. Thank you. The organization team, and as well as all the participants. I'm Dr. Rakesh Jha from IIT DM Jabalpur. In today's lectures, I will give the practical scenarios. Those have already performed my lab, 5G IoT lab, in real scenario. So my outline of the today presentation is introduction, why energy efficiency is really required in current scenario for the 5G or beyond 5G networks, motivations, general architecture for relay selection and device-to-device pair. And the last sessions, one of the students has asked about is there the requirement of machine learning at relay selections? Yes. So I will give the details also. At the same time, as per time limitations, I will do the analysis of case 1, case 2, and case 3. One case is very popular because this one is sector-based radio resource allocations. After the sector-based radio resource allocations, I will give the idea about novel beam breathing approach using artificial intelligence. And in the case 3, journal-based green communications, ZB Green. All the work has already published and in transactions. So, and last one, green and safe 5G and beyond 5G wireless networks. Before we continue from my introductions, these days you people are really observing when you are using your mobile phones and just thought or just ask the questions to your sisters or mother, if they have the small children in their home, they are complaining about the itching phenomena, right? And they are also we peoples, the elder age peoples also, uh, uh, the sweet yeah, phenomena is not appears in last 2 3 years, because due to the high frequency approach, now radiations is very very big challenges for the researchers. When you will go for the bath, you feel body has different type of itching. We thought the water is dirty, but practically we have done the survey on near about 300 students, as well as the faculty. We found that there is no only difference is it depends on the only the water impurity problems, but that is also problem with the high frequency communications. So is my slide is visual, right? Yes, my slide is visible. Someone is
Yes,
asking
that is
what
visible.
about the slide? Yeah. So that is the real challenges for you peoples. In the last sections, we will also discuss about some the future research challenges. As far as the green communications, researchers is always thinking about 1G, 2G, 3G, 4G, and beyond, now 5G and beyond 5G. And in 2013, I was given the idea about the 5G architectures, and I was also mentioned in that paper about the some a small cell access point can be replaceable at the positions of Wi-Fi. And in the future scenario, we have also given the idea about what are the frequency can be possible for the 5G. So currently at the same near about approximately same 750 megahertz and 28.8 gigahertz, the band is allocated for the 5G testing. So the researcher is only looking for high data rates requirement, high data rates. But now is very important aspects for all the researchers regarding the green 5G or green networks, green next generation networks. So this work is all about the green or energy efficient machine learning based 5G communications. Now, as we know that due to the large number of subscribers, we thought every person nowadays have one person have at least two phones or one phones with a two SIM. I think you all are agreed on these points, and we are near out cover the entire population near about 60 to 70%. So you can understood how much number of subscribers is increases these days. Okay, so that is leads towards the densifications. That's why the 5G enabled with the ultra dense network, UDN networks, right? So if the densifications will increase, then ultra dense network is an important part of this. IP traffic will reach 500 exabyte by next year's. Extreme densification of base stations. Say at the same time, if the number of users increases, so the number of towers, that will base stations, is also increases. So since if we increases the frequency, so reduces the cell size. If the cell size reduces, you know that the frequency increases, the signal distance will decreases. So you can compare with the range of the communications. Initially 12 kilometer, then 8 kilometer, then 4 to 6 kilometer, then 3 to 4 kilometer about the LTE and LTE advanced. Now for the 5G, near about 1 kilometer, so 900 meters. So if the cell size is reduced and the number of users increases, then spectral efficiency is the important part. So when you will analyze when you will do the some preference analysis, please understood why spectral efficiency is the main parameters for the preference analysis due to this. Now, since base stations is not enough to provide the resource allocation to all the users, so what can do? So yes, so relay came into the pictures. At the same time, one another remarkable the part of communications in LTE or 5G NR is device-to-device communications. You can able to see device-to-device communication. You can able to see alternate network and spectrum sharing. I heard one question about the spectrum sharing. We have done some work on spectrum sharing, and in one point, let us assume that one user is A and other user is B. Okay, so if let us assume that here is A and other user is B, right? And they are both are communicate to each other. Let's assume B now is reach here, right? And A is here only. So maybe the C will help to reach them, right? To reach them. Either if all the network will belongs to only one category like 4G, 3G, or 5G, it's okay. Otherwise, if one A to B is 4G and C is using Wi-Fi, right? So the band is different. So that's why the spectrum sharing is very important. So if A will A send the information through C, so now there is a big research challenge for the future scenario in the spectrum sharing is the security approach, because C might be connected with the D and D will be eavesdrop the packets. So the first question is spectrum sharing is depends on you are doing with the homogeneous networks or heterogeneous networks, and on the basis of this you can allocate the spectrum with their machine learning. So yes, machine learning is very useful in this case also. At the same time, beamforming, how the beamforming will be served in the current scenario. I will discuss in details in the one case study. NOMA, I was proposed NOMA MIC, non-orthogonal multiple access, multiple interference cancellations. So what are the difference between OFDM and NOMA? Since base stations is now these days is very smart, right? Very intelligent. So they have all the channel information, channel coefficient of I will again explain. So let us assume that here is the base stations, right? And here is the user A, user B, and user C, right? They will send the channel allocations for A to B, B to based on to A, B to based on to C, based on to D, and all the channels is equipped with the channel coefficient H1, S2, S3, right? S3. So regarding the NOMA conditions, currently S2 will be interfere with H1, S2, S3 will interfere with H1, H1 interfere to S2, S3 is the interfere with S3 will be interfere with S2. So this type of scenario in the case of NOMA, right? In the case of ODMA, although there has a orthogonality maintained, but this type of problem hasn't appeared in ODMA. That's why the NOMA has the playing the big different with a very important roles. How? Since base stations have the database, now on the basis of training, they understood which type of channel coefficient of H1, H2, S3. So they will arrange the channel coefficient, right? And arrange the channel coefficient. So if let us say H1 is lesser than S2, lesser than S3, right? Or S2 is we will place last, S3 is second. So in this case, S2 is the highest performance, better channel as compared to other one. So base system will directly allocate to S2, and at the same time they will restrict it H1 and S2. Once they will allocate this, at the same time they will block this, right? So in the last lectures, they have sir has already given the idea how the block, but I am doing the analysis the practically how they are actually performed in the real time scenario, right? So once S2 has allocated, after that which one is better? S3. So after this S3 will be allocated, right? And then H1 on the basis of priority order. So if we will do the training of the if you are doing the performance analysis with the training base, then you can able to remove the interference in the case of DMA using NOMA. Okay, and at the same time we have also proposed in NOMA multiple interference cancellations. we will discuss in later phase. Yeah. Abhishek, please, please, I'm audible. Then please ask the questions. How I can able to see the chat box? Is I'm audible? Yeah, please ask the questions.
Participants, you can raise the query in the chat box as well as in the Q&A section. Rakesh sir, there is a question. In OFDM, orthogonal subcarrier frequency, so how there is interference and NOMA removes that, sir? Sir, you can see in the chat box, is it visible at your end?
Hello, sir.
Yes, Abhiranjan, you can raise your query.
Sir, in OFDM, orthogonal subcarrier frequencies as there. So in means all users are in orthogonal subcarrier frequency. So there is no interference, but there is interference because of some imperfection. So how NOMA is overcoming that? Because NOMA in the same frequency band, all users are connected to the base station. Means I am confused. So please remove my confusion.
Abhiranjan, I'm audible?
Yes, sir.
Yeah.
Now,
So, yes, I'm audible or not? Please.
sir, now, sir,
Yeah.
now, sir, audio.
Yeah. So, Abhiranjan, in practical case, where the base station is there, and let us assume that user A, B, and C are there, right? Right, Abhiranjan, Rakesh, and the third person is there, right? Now, at the as per your demand, let us assume that A is requested for voice applications, B is looking for the text applications, and C is looking for the video applications. Understood, Abhiranjan? At the basis of your demand, base stations will be allocate the subcarrier, right? Subcarrier to you peoples, A, B, C, right? Now A and B and C all are active at the same time with a different frequency, right? At the same time, they will allocate the different carriers. So A is looking for the 15 kilohertz. Let us say that B is looking for the 30 kilohertz and C is looking for the 45 kilohertz. So due to the different subcarriers, for 15 is required, let us assume 1 millisecond. 30 is look at 2 milliseconds and 45 is the 3 milliseconds, right? Understood? So at the same time, all users are demanding to the base stations, so fulfill the 15 kilohertz. At the same time, your video and voice is also active, at the when text application has been converted, then your B and C is active. When B is active, then C is active. So at the same time, B can be interfered with the A and B can be interfered with the C. So this is the conditions in the case of OFDMA, because
Sir,
OFD,
but they are on different sub-carrier frequency, na, sir. Different frequency slot, na, sir.
see what practically happened. My slide is visible.
Yes, sir. Yes, sir.
So sir, how I can write how I can write this animations? My slide is visible or not?
Yes, sir.
So, how I can write? Organizer, can you help about because my pen is not visible. Just a minute. Share my screen. Okay. So that is I think okay. Now is okay. See, I mean here is the base stations. Okay. You are A is here, B is here, and C is here. Okay. Now there's a radio link is there for 45 kilohertz. I am audible. Beto, please be online.
Yes, sir. Yeah.
30 and this is 15. Okay. So you will demand request packet is there. Request. Okay. Request is in uplink. Understood?
Yes, sir.
At the time after the request, since there is a band, and in this database subcarrier band, you will allocate looking for this, other one is looking for this, and third one is looking for this. Okay, Bitu? So different
Yes, sir.
frequency, but there is a radio channel. Understood? This is a radio
Yes, sir.
channel. Radio
Yes.
channel is air,
Yes, sir.
anywhere, anytime. So at the same time, when they are looking for this, right?
Yes, sir.
If
Yes,
this
sir.
user is in their range, they can interfere their channel, and they can be interfered the channel, because all the noise has a nature of additive in nature. I mean,
Yes, sir.
understood?
Yes. Yes,
Right.
sir.
But if you, after the machine learning, you will apply the machine learning, you will give the training of this base station in such a way, those have the different, since A, B, and C is there, all have the different channel coefficient.
Yes, sir.
Understood? And now you will apply the rule after the training. If H1 is better than S2, S2 is greater than S3, then you can give the priority. You
Yes,
can
sir.
serve with the different time slot, right? We can give the priority. So my fraction of second is different. So at this time in the NOMA, after the priority, once the training has been happened, they can categorize the channel coefficient, and then they will allocate. So there is still there is a chance of interference. I will explain later, but you can somehow decrease the interference in the real time scenario. This is the real time scenario. You are talking about the different frequency, different time slot. That is not in the air, right? In the air, everyone is independent to take the to participate the channel. Understood?
Yes.
Understood, Bitu? So
Yes,
this
sir.
is the real time scenario. Okay. So hopefully you understood the.
Yes. Yes, sir.
Yeah.
Yes,
So
sir.
impact of the on the society of this green communication is reduced carbon footprint, ecological balance, higher operating time of the base stations, fuel saving, and this is very important. Our one word has increased the battery efficiency up to 43%. I will discuss and you can go through my papers. Now these days it's very most challenging part is battery lifetime. Understood? All the participants are agree. Everyone is looking for the battery charge. Where is the mobile charging point? Due to this, right? So there is some phenomena you can decrease, you can enhance your battery lifetime. How? We can see. So one participant is also looking for the spectrum sharing. I will show how the battery time can be enhanced. So through this, what are the motivation of green communications is quality of service and quality of experience. So anyone can explain about the quality of experience? Have you heard about anyone? Quality of experience? Any participant can give the answer about the quality of experience. What do you mean by quality of experience? And quality of experience is directly deals with the mean opinion score. So let us assume that you are the service provider, network service provider, NSP, Airtel, Jio, Vodafone, anything. So how they have, in India is very, I don't give the name of anyone NSP, but some network providers still are doing one network service provider. I will not give the name. They are basically looking for the mean opinion score or quality of excellence. Let us assume that they've done the survey on the 5 persons, and 5 persons. There is a one chart they will provide to please give the marks 1 to 4, 5, right? And if the average score is greater than 4, then it's we can tell this is okay, right? And 4.5 is good, and 4 point greater than 4.5 is excellent quality. So quality of survey, quality of experience is very, very important for the any wireless communications network. Okay, now I will move towards today's agenda. At least one novel approach I will show that is really providing a great platform for the 5G networks. So propose an architecture for green communication in 5G wireless networks using device-to-device communications to allocate the radio resource to the device-to-device user in network for such quality service and quality experience, and achieving the green communications. And last one is green and safe wireless communications, right? So the question is, why device-to-device communications, practically implemented? So in the future, currently, let us assume that here the base stations, right? Base stations look like this. Here is a small cell access point, a small access point. Here is some relay, right? And here is the device-to-device pair or some single users, right? So currently, you people are directly getting the signals from base stations, or if you are in the cell boundary, to inform the coverage, you will receive the signal from relay. So relay is somehow not bigger like this. So you are here, so they will get the information from here, right? You are here, or currently in the future, all the maximum communication will be happened or take place through the device-to-device communications. Okay, so device-to-device communication is nothing but if the two users is distance between less than 30 or 25 meters, less than 20 meters, then they can take part of the device-to-device communications. But the question is, why this user will serve the link to A, why A will serve the link to B? Anyone can define? So the same question asked by to me when I have submitted for the RFC for this case study. So what are the scenario? If A will if A will provide the link to B, then their battery lifetime will be decreased. Understood? The battery lifetime will increase because they will serve the channel for for B. So how A can participate provide the channel to B instead of base stations can provide directly to this. Base stations will provide the link to A, but A can provide the link to the B. How and why? So initially, when we have done the survey on only 15 students, all has denied. All has denied. No, sir, I will not take participate on the device-to-device communications. I was asked why you people are not take part of the this device-to-device communications, because he told, sir, if I will communicate A to B, I will communicate to B, then the battery lifetime is will be decreased drastically. to this handset. So I will give the one idea. Let us assume that A will give the award by the NSP or base stations award by the Q learning or any algorithm. The practically is if A will get the award, which type of award? They will get the 5 GB data, 5 GB data on the per day or 1 month, what other things are there. Then I will tell him, okay, Mohit, you will get the 5 GB data and you will provide the device link to the second users in throughout the day is 1 hour. Okay, so they then after 30 minutes, 20 minutes, he told me, yes sir, now I am agree. So this is the case. You can provide the award. Actually, in practically, you will provide the award such that they can take part in the case of. So you understood what are the things of award practically associated with this learning process. So this is the case study of device communications. Practically, you can also do or gone through the many researchers. Research papers have been available in the IIT transitions or survey tutorials. Okay, so this is the one strategy you can do the any work with the practical scenario. Okay, now those are very new in wireless communications, or those are very really expert. I think there is no use of this artificial, but those are looking for the researchers do the research in this field. This is really good platform for you people. So here you can see this is the base stations and this is the 5G scenario. I already told the radius of this 5G scenario is 500 meters, right? So here is the base stations, right? Now they will directly provide the link to these users. They will directly provide the link to these users, right? Line of sight, null line of sight, you can already you already understood. But here the user is here, so they can not take part the directly link here. There is no link, so relay can be can provide the link to this. Here a small cell access point. A small cell access point is nothing but the Wi-Fi hotspot for the 5G communications, and they will provide the link to the inner user. So I will provide the one basics hidden model proposals. So let us assume that please unmute any one participant who is doing the work in wireless, so that they can provide some idea to me. Anyone, please unmute, so that you can practically understood how the transitions rule machine learning is applicable in this wireless communications. So anyone can unmute. So here, let us here the base stations, right? Direct users mark as a B. In the relay can be marked as a B, and a small cell access point marked as a C, right? Okay. So as you know, Hidden-Markov model is based on the Bayes rule probability-based approach. So as a general, if base station will assign the probability, base station communicating probability with A, B, C, out of A, B, C, which one is the highest priority? Anyone can tell, and why? Then you can understood. Otherwise, there is no meaning.
C, sir, C.
C, very good. So who is who told? May I know name? May I know your name, please? Or please unmute itself. Abhi, please be online so that I will take the
Yes,
some.
Aviranjan, sir.
Aviranjan. So C, why C, Aviranjan? Can you explain?
It has more number of users,
Yes.
sir. It is a access point. Small.
Yes. So more number of users can be communicated by the C. Or second number, Aviranjan, who is the second number?
A?
No. A is the single user, right? Relay can provide the more than one link.
Relay, sir. Relay.
Yeah.
It providing two user.
2 user, 3 user, maybe,
Yes,
right?
sir.
So yes. So probability of assigning from A to base station to to a small cell access point is higher than B and then A, right? So this is the yes, very good. So this is the actual probability assignment when you will do the actual process. So thank you. So what are the flowchart iterations in this case? So you can create the creation of initializations and creation of the solution scenario, generation of random user and SCA. Random always try to in initial phase you can take the fixed node fixed number of SCA and users, but the practical scenario you always consider as a random scenario. So how the relay selections can be happened, I will prove in this case study, and we will apply the hidden Markov model at base stations, a relay, and a small cell access point, right? And then we have done the result analysis. So see what happened. So with the mathematical modeling, you can go through the papers, but I'm here for provide some basic knowledge to you people. So here the layer architectures, how the layer architectures has been happened. So see, this is the layer 1, this is the layer 2, and this is the layer 3. You can observe Avranjan, here the color. You are able to see the color, different color. So what happened if the base station is here? Practically see, base station is here. If you are here, Abhiranjan is A is here. Now after some time they will move here, and after time they will move here. And I am the base stations. So Abhiranjan, which case the power is required is high?
So, the user which is very far from the base station,
Yes.
it will require more power.
Yes. Yeah. So general is very far from they required large power. Or at the same time, if one cell has one user, other cell has 2 user or 3 user, and one cell have 50 user, they can also be the condition. Understood?
Yes, sir.
Understood or not understood? So when your machine learning or your database training is required, if only one case is there any requirement of training? No.
No.
If more than one condition will appear, then you can apply the case study or training, right? So why this color is happening? So always remember that reddish color is required higher power. Green color is very less power. Everyone understood? Or
Yes, sir.
or and if the power is between them is like blue or like this. So always remember that when you will do the layer architecture or anything, there is some sense of your proposals, right? So all the participants understood this. Why this layer, different layers are there? Because due to their because I am dealing with all the preference size on the basis of green communications, right? Or energy efficiency. That's why I am here taking care of this, right? So green is okay, blue okay, and this is the light is pink. Or if they will become the very dark, right? So that is very large number of powers. Okay, so this is the general sense of this. Now there is some general scenario parameters, and all the parameters how you can consider. So we have also contributed some real-time analysis, but at the same time you always please try to understood, always considered ITUT latest release is 19 or 20, right? Or you can consider 3GPP, 3GPP, third generation private partnership, right? So always considered when you will do the work in wireless communication, always refer only these standardized parameters. Please don't follow my papers or any papers. Always try to follow the ITUT and 3GPP standardizations, where they have given the case studies one by one. No doubt, the actual article is near about 700 pages, 300 pages. So please don't worry. You are looking for your case study, right? Or general case study. But always looking for this 3GPP release and ITT release, right? That is very, very important. Now, 31st December, they have released the VLC in cooperations with your 5G, and satellite communication also going to be the part of your beyond 5G, that means 6G communication. So how you can understood through 3GPP, IIT, and if you are very good researchers, you can also refer RFC, new release of RFC, right? Request for communication. So that is the important part. So what the parameter we have considered is all are based on that time of IIT release, right? Now the first relay selection strategy, after we have applied the hidden Markov model. So based on SNR threshold, path with the minimum power is selected. That means which path will be selected, those required the minimum power. Okay, and the base relay selection based on minimum PR plus PS. PR is relay power and PS means source power. So once when we have done the iterations 1, so see iteration 1, relay power, iteration 2 and iteration 3, we have done the 3 type of iterations. So in relay 1 is required 3.26, 2.67 in relay 2, and relay 3 is 2.89. At the same time, when iteration 2, this can be varied because random selections, the user can move. Sometimes user is here, sometimes user is here, right? So base station is still fixed. So if the power required here is 1 some point something, what? So this here maybe 1.5, that is 1.5, 1.3. So if the distance is higher, okay. At the same time, source power, the base station's power in iteration 1, 2, 3 for the relay 1, sorry, iteration 1, relay 1, 2, 3 is look like this, right? So the total power consumed in this process in iteration 1 is 8.97, 8.22, 7.63. In iteration 2, 6.94, 7.45, 8.20. And iteration 3, 8.39. Avranjan, who in iteration 1, which one is selected? Which relay is good? Which relay is good?
Relay which require less power, sir.
Yes, relay is 1, 2, 3 here. In corresponding to this, here is the total power 1, 2, 3. So which one is selected? Lesser power. So which one is lesser? Which relay?
3, sir. 3.
So iteration 1, you will select the 3. And iteration 2, which one is selected?
1, sir. Relay number 1.
Relay number 1, right. And in iteration 3,
least power, relay number 3.
Yes. So again, so random selections at the basis of on the basis of channel selections, on the basis of power allocations, this is required. This is the way you can select the relay selection. So one student has asked something. Just how I can able to see this chat. Hello sir, the end give us the insight to read. Understand the 3GP release. Yes. 100. Yes. So I will actually open the release and then I will tell you. Okay. So if in the last order I can tell now. If I don't know what are the things to you last I think. Okay. So please remind me. I will provide the actual concept related to 3GP and IIT release. I will open the file PDF file and give the idea. Okay, so as per Avranjan, here is a relay 1 selected, here is a relay relay 3 selected, relay 1 selected, and relay 3 selected. You can provide the result on bar as a bar chart also. Okay, no issue. Now, so power allocation strategy based on hidden Markov models, dynamic power allocations, and you know that this process is a stochastic process. So on the basis of the probability, you can compute this, right? So this is the general scenario in my first case study. Now, one thing is very I'm really interested to you provide this data to you people. So I don't know the name of other person, so Avranjan, please be with me, so I can. Sir. Yeah, I will provide one very good idea to you people. So here's the base stations. So you people can also give some noble approach to the country or the world. So here here is A, here is a B, here is a C, right? Currently, I am teaching about the AMC, modulation coding AMC, how the modulation AMC has been selected in 5G or your LTE or LTE advanced, right? Or Volt LTE. So here's the base stations, right? Right? And the question is how, which modulation scheme will be A will receive, which modulation scheme will be received by B, and which modulation scheme received by C on the basis of machine learning these days, or on the basis of training base. So understood this. Here, A is a B, A is a C, right? So, Abhinandan already told, base station will send the information to C, the required larger power, and lesser power is here, here. Now, initially, let us assume that we compare with the BPSK, then QPSK. I'm just taking the examples better, and then QAM, right? BPSK, QPSK, and QAM. So, which one has assigned QPSK, which one assigned the BPSK, and which one assigned the QPSK? How anyone can tell me, please, how the basis can be decided? So that it depends on applications A1, A2, and A3. First application, first is depends on applications. What the applications? If A3 is looking for the video applications, and now these days the buffer is not required because buffering hoga to karoge nahi. So buffer, there is no requirement of buffer. So you are looking for the high data. So one symbol required large number of bits. At the same time, if voice are there, yes, still there is no requirement of delay, there is no latency is permitted in this case. Also high modulation scheme. But in the text, delay can be permitted. You can provide the load modulation scheme. The first requirement is there. Second requirement, the practical requirement. Okay, let us assume that C is looking for the video applications, and they are watching movies or online cricket. So they are looking for the 256 QAM. 256 QAM. Right? Is this possible? And C is here. C is here. And at the same time, the same B is also is looking for the 256 QAM. And A is also looking for the 256 QAM. Let us assume that you are the base stations. Which one is the perfect conditions base stations can match? Which one is the base conditions and why?
So C is in video application. So
no,
it requires.
Let us assume that all has looking for the video application. All is required the video application. All are watching cricket live. So base stations, which positions base stations can provide easily the 256
nearby.
Why? The question is why? Because this is very, very important. Anyone from
line of sight? Low.
Let us assume that all are on the line of sight. All are on the line of sight. So see, Ranjan, you know the structure of I am here. I'm putting here. Then I will move again here. So let us assume that one bits here, one bits here, one symbol in QPSK here, 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 256 or is 816 ले लेते हैं, ये बहुत complex हो जाएगा. So please understood this. Four. So this is which modulation scheme?
For QPSK.
And this one
16 QAM.
So now see the threshold between 2 point, threshold between 2 point, and threshold between 2 point
Decreasing, sir.
decreasing. And noise, if noise will appear, noise is always additive in nature, right? So any type of noise will appear. Which one is the less affected noise?
BPSK.
This one. After
Yes.
this, and this is more affected.
Yes, sir.
Understood? So as a general case study, if the base stations is very far here, so here which modulations you can apply? And
BPSK.
BPSK or QAM. But if you are very lesser distance as from the base station, then which modulation can be served? 256 QAM or 16 QAM. Understood or not? Because if the threshold between the two bits very low, then noise impact is very high. Understood? So practically, Abhinanjan, understood or not?
Yes, sir, because the threshold
Yes.
will be less affected by the noise.
Noise.
The nearby.
So yeah, so A can be incorporated with the higher modulation. This is the middle type of a modulation scheme, and this one is the lower modulation scheme, not BPSK, QAM, but lower QAM. So practically, how you can justify this? So when you are away from the base stations, please switch on your mobile and see. Currently you are receiving, when you are nearby the base stations, you are receiving LTEA or volt LTE. When are far from somehow far from base stations, you are receiving HSPDA. Have you understood or not? HSPDA. And when you are very far, then there is a 3G or something. So why this happened? Because when you are very close, basins can be able to provide the high modulation scheme. When you're very far, then techniques also change and modulation scheme also change. Understood, Abhinanjan, or not? So
Yes, sir.
on the basis of distance, on the basis of applications, your modulation scheme has been changed adaptively. That is known as adaptive modulation encoding. Understood? So this is the case study you can understood. Okay. At the same
Yes, sir.
time, this is at the same time you can also see here now practically. Isa, Akansha, I think now we understood. Yeah, set A. Why set A? I have given the proof. Okay. Now you can able to see here user distance. So see, if the user distance is, let us say user 11 and distance is 27 kilometers, 27, and power allocated is 14.9, 12 is your distance is 22, and 4.5 power allocated is 4.5. So what is the condition is there? So power and distance and model scheme are very incorporated, right? How both are very important. If the distance is very far, power is required for high, right? High power is requirement. And so how we can prove this? So user distance 338, here the power is 62, 230, 41, 92, power is reduced, 37,
6.4.
and 28, 1.5. So that is also depends on your the distance. At the same time, they say also depends upon if the distance is very higher, which modulation scheme? BPSK. When the distance is lower, then move toward the QAM, BPSK to QAM. So this is the actual analysis of the base station. You will do the all types of research and everything, but practically how the modulation has been allocated by the base station, this is the case study. So hopefully you understood how we move the next condition. So this is the same what I have done, power allocations. So through hidden Markov model, if you will apply the hidden Markov model, you can save the power drastically, right? So how this can be happened? So initially what happened before the machine learning, let us assume that here the base stations, A is here and B is here, C is here. Now A is looking for the some link, right? So let us assume here the 20 watt, 2 watt power is required, and 2 watt power is looking for by 3 users. So this can be simply divided by 2 by 3, right? Watt, simply. So this type of algorithm is known as proportional algorithm, right? So proportional value has been allocated, proportional power, right? They are not able to see the distance, they are not looking for the applications. But when you will apply the hidden Markov model and you will apply the condition with the distance, applications, then you can see here this much power is required. All case, this power is required. But in the hidden Markov model, if the application is very high, video is okay, give higher power. Voice, give higher power, somehow higher power. Other case, no power. So this is the great advantage of the machine learning in gain communications. So hopefully understood this case. Now, since that due to the time limit, I will show some real-time case studies of my important submissions. So I will move directly about sector-based radio resource allocations. So, but what is the sector-based resource allocations? So, see, till now, what happened? Here is the base stations. You are able to see the base stations. Now, ultra-dense network. You are able to see the ultra-dense network. Here the base stations. Here the ultra-dense network. Here the device-to-device pair. Here D2D pairs. Now there is a one very important concept for you people those are really doing the research in wireless communications. So 180 hertz kilohertz band with the 20 subcarriers. Initially, one people has asked how sir interference can be minimized. So 12 into 15. One subcarrier is allocated with the 15 band. So 15 total band is 180 kilohertz. So what currently what are the things are going on? Initially, 80 kilohertz band is allocated for all the users. If you will if A is demand, B is demand, or P1, P2 is there, P3 and P4 or Pn is demanding. Let us I am looking for A applications, A1 applications. This is one is also looking for the A1 application, and this one is looking for the B1 applications, and this one is looking for the B3 applications, right? So initially, what the base station has done, they allocated the entire 180 kilohertz band, entire 180 kilohertz, all the users. But in my proposal, what we did, we use, since we understood that one concept of frequency reuse, the same concept we have used in 4G LTE and 5G, we have used the resource block reuse. What's the meaning of resource block? Let us assume that A1 is looking for the only 20 subcarrier. This is looking for the 14 subcarrier. This is looking for the 60 subcarrier. This is looking for the 50 subcarrier. So what are the currently things are going on? Once you will demand request to the base stations, they will allocate the 180 kilohertz band entirely. So how much wastage? Anyone can tell? Here 160 kilohertz band. How much here? Sorry, subcarriers band. Here how much? Abhinanjan, here how much waste? 180 required is 40, but looking for the
140 kilohertz, sir.
140. Here is 120.
120.
Or here is 130.
30.
So see, Abhinanjan, in one iteration, if only 4 users, you will lose these amount of subcarriers. And you understood, subcarriers is not a you will allocate and they will destroy. No, they require power. If you are looking for the 100 subcarrier, required power is P. If you are looking for the 200 subcarrier, P dash, and P dash is always
2P,
greater,
sir.
right? Or yes, 2P, or that is always greater than this. But what we did, we used this resource block. Let us assume that they are saving 160 subcarrier. So the next time next time if the user in D2D pair, so it will not demand it again, because in the request time also your power is required, right? And mobile station, your mobile device is required higher power when you are looking for the demand. So why, how much time they will not demand it again to the base stations till this exhaust, this 160 subcarrier is exhaust. So in the next iteration, this pair will not serve by base stations, this serve by this, because they are looking for only how much subcarrier Betu? 40. Understood? So 40 again, let us do that. Here one subcarrier pair will come, they will provide 60. So up to R minus 1. R minus 1 means 180 minus 1. One subcarrier is required. One subcarrier is required for demand, right? For demand. So up to this subcarrier, they are not demanding to the basis, right? So this is known as the resource block reuse factor, resource block reuse conditions. And what we did, we have divided the entire sector into sectoral based. So what are the advantage of sectoral based? There is a limitations of interference, because at the edge they cannot interfere here and there, right? Here and there, because we have divided the sectors, right? We are dividing the sector. So through this way, we can reduce the interference, as well as on the basis of resource block reuse, you can achieve high energy efficiency condition in 5G wireless communication. So understood this the concept. Now there is some mathematical conditions. This mathematical condition you all understood, the Shannon-Hartley law, and on the basis of Shannon-Hartley law you can compute the channel capacity. But one is important thing. This is the maximization problem. When you will do the reinforcement learning or Q learning algorithm, you should be decide the threshold, and on the basis of threshold you can maximize the power, right? So on the that conditions you can able to achieve the high capacity or energy efficient conditions. So since do the time limit, I will see some result only. So here the cellular user is one, pair 1 and pair 2. So this resource block, if not uses, they can be reused. Again, see, entire resource block can be used. Entire resource block can be used. So in the different iterations, they can reuse the resource block. So on the basis of this, what the advantage? So see here, our performance analysis is very remarkable, because this performance on the basis of SBR array, we have achieved more throughput, more quality of service, better quality of service as compared to hidden Markov model, right? So you can able to see here, find that device to device pair is 2, resource block calculation with HMM, and resource block SBR array. So in all the cases, this one is better performance as compared to machine learning. So you can beat the machine learning also with some novel techniques and apply the machine learning. So you can have the better performance analysis as compared to machine learning approach. Okay, so what are the case here? Let us assume that A1, A2, A3. A1, A2, A3 is the applications, voice, video, and data, and you are able to see in all the cases your SBR array have the larger throughput as compared to your HMM. So one question is very, very important. You understood here the throughput is Mbps, but we are looking for the data rate throughput in Gbps. So what are the difference between 4G and 5G? Anyone can tell me why suddenly the your throughput will be reach up to 1 Gbps or greater than 1 Gbps, because in 4G 20 megahertz bandwidth is considered, but in the case of 5G the testing condition 750 megahertz. I was projected in 2013, and the same 750 megahertz band is going to utilize at 28.8 gigahertz. So when you will multiply 750 megahertz, that will be reach up to 900 megahertz, 900 Mbps or 1 Mbps. So what are the conclusion? In the last in beginning, I told there's one parameter known as quality of experience. So how we can measure the quality of experience in this case. So the maximum quality difference is 4.5, right? So see here, if the device were 2, if the device pair 3, if the device pair 4, in all the conditions, see, in 1, 4.14 and SBR array 4.83, and we can reach up to 4.9, right? So through current infrastructure, if we will apply the SBR array, we can enhance the quality of experience of the users. Quality of the users, how can calculate? On the basis of survey, right? And there is a one parameter we have also defined, and this already mentioned in this paper. Sector-based radio resource allocation algorithm for better quality of service and experience in IEEE Transition Vector and Technology. So you can refer this paper for the details, right? So if the user is in the two nature, distributed and concentrated, if the user at the same time all are moving at the same position, then complexity will increase, right? So that's why here we initially when we have proposed this approach, and we have discussed about this. Sometimes without SBRA, that means HMM is better than in some case as compared to this. Why this happened? So initially thought we will drop this idea because complexity is higher at some point, but no, this is appeared due to the high interference in SBRA, because sometimes when the users is concentrated and form is an ultra-dense network, then in that case complexity is higher as compared to HMM. So always try to, what the results you got in your performance analysis, try to put on the same environment. Don't think forcefully or no, my result is wrong like this. So because due to the ultra-dense network in nature in 5G networks, might be machine learning or AI can be sometimes for better performance as compared to the approach. So this is the case studies for this. Organizer team will tell me is I'm continuing or continue or shall I stop or take the questions?
Sir, how much sessions are left from your end?
I will take 2-3 minutes
Yes,
for.
sir, you can continue, sir. Thereafter, we will give a lunch break, sir.
Okay. So I will take only 2-3 minutes for you people who will do the research in beam forming approach. So beam breathing, you will take the inhale the breath like this. So let us assume that I will give the examples and then tell you. So here deep breathing, what is the approach? So here the base sessions. Now user is A is here and user is B is here. After some times user A is moved here, right? So let us assume that beam forming, you will produce the beam look like this, and bandwidth look like this, and directivity look like this. But when the user moves here and cell of the base station, so what will do? Anyone can tell? What will do?
Beam has to be transformed.
So what will do? You can reduce this. कभी आप बेंडिंग वाले के पास जाते होगे तो देखते होगे कि उसका initially the beams of that bending is very broader, but when we'll do the some bending with the some distance
Narrow
approach,
narrow
yeah.
bending.
So yes, so we'll reduce the
Beam
so
width.
yes, so here the beam is here, but we will reduce, they can reach here, right? Understood? But let us assume that okay, so A is okay. Now B is here and C is here. B and C is also there. If we will do the beam, the activity look like this, right? So what happened? Then what happened? What will do? B and C is not able to receive the information. Then what will do in this case? Anyone can tell me?
Interfere, sir. They will interfere.
No. Provide the solutions. because always looking for the solution. That is, here is base stations and you are here. So initially beam is look like this. So I narrow this, I will reach here, right? I will reach and provide the link to you. But here is B and C is there. Then what will do? Because
we
you are
will
not.
send
Tell me.
another two narrow beam to B and C.
Yes. Okay. So we will send the
Another
other
two narrow
beam
beam to B and C.
and C. Right? Very
Yes.
good. And here D and E in between them. Then what will do? One approach is very good. So is okay. What will do?
So we cannot use the same extended beam forming that is assigned to B and C to D and
So
E.
what are the solutions? Thank you. So what will things? We have proposed one idea. We can merge this beam. We can merge this beam, and this is known as beam merging phenomenon. Understood, Betu? We
Yes,
can merge this beam. Now beam look like this. One beam is look like this, and other beam is look like this. But after merging, they will directivity as well as the broadening both. Understood? So what happened when we will do this? So if the user density is very high at the cell side, then directivity will increase. Understood, Betu? But if the cell users is very larger in the position middle of the base station, let us say that this is a cell, and if cell here the base station, which phenomena will use? Directivity, right? And merging. But if the cell use, if the mobile user is here very near to base stations, but one beam is not able to, the activity will not provide, then we can use the beam broadening phenomenon. So understood? Beam merging and beam broadening. So how beam merging will be take the part? So here, this is the base stations. Alternate network is here. So you can reduce the directivity. Directivity reduce करोगे तो क्या होगा? Press करोगे, and when press the beam, they will suppress like lubricants, right? So user can large number of that, users can be now served. Understood or not, Betu?
yes, sir.
So this phenomena is known as known as beam breathing. Beam breathing मतलब कभी आप क्या करते हो? Inhale and छोड़ते हो, right? So sometimes if the user density is in the middle of the base station, then you use the beam broadening. And if the users will be at the boundary edge, and if the density is very high, then beam merging phenomena or directivity can, right? So this is the actual case we have done in the real time scenario. So this is the university where we have done this performance analysis. There is a bank sector, so we will move the users, and how you can yes, some people are doing the research. So if you are using the Airtel networks, so there is a one key that is known as open networks. So in open networks, when you open the site through the Airtel open networks, you are able to see the actual map, and you are able to see the basically the base station had deployed or users density can be deployed. You can able to see, right? Open networks. Anyone are interested to do the real time research, you will see how the beam is moving towards your end, right? And once you will get the beam, you will map with the Google Map. So this is also supported by, we have given the credit of Google Map. So once your beam will be merged with this, open networks with this Google Map, you are basically plot the actual environment. So we will see the Jammu, J&K bank area where the density is very high, but distance is very high. But here the BC junction who are there, but the area is very close, right? So when you are able to see when the user is very larger distance, you will see so the beam directivity increase, and when the user is lesser, then we will use the beam broadening. And if the user density is very higher, so I was asked with one candidate, if the left, some users left, then what will do? Beam merging phenomena. Understood? anyone in there, then please let me know so that I can conclude here. Okay, so this is from my side. This is the implementation part. The main part is how you can think in a noble way and propose something for the. So this is from my side. Please ask the questions. Does beam merging leads to decrease in that? Yes, yes. If when we will do the beam merging, the activity can be increased, but the proper SNR can be achieved, because SINR is the first quality first parameter where you can able to calculate the capacity, and capacity leads to the all the factors. Please understood. First, calculate the one thing is very, very important for all the researchers. Please understood. First, always calculate the channel coefficient. Channel coefficient, after channel coefficient, you can calculate the channel gain. Once the channel gain calculated, calculate the SNR, or then calculate the SINR. Then calculate the capacity. Then calculate the energy efficiency. Then calculate the spectral efficiency. All are related. This is the flow. Please, all the researchers remember. And not there is no any noble things, but this is the proper you can anyone can calculate, and you can do the research and provide their nobility for the world. So always when you will do the work in wireless, please understood what are the nature of the channel, practically understood. When you will put the glass sheet, when you will put the wood sheet, what are the impact are there? If we will apply, when you will apply the, someone telling I'm really fading here, you can propose your channel model. Just put just read out the basics and put your condition, right? Very, very easy to do, very, very easy. And after SNR, you can calculate, previously we thought about the BER analysis and that. Yeah, my mail ID is, jharakesh.45@gmail.com. I was the first person who has with Repaport and proposed the 5G architectures in 2013. After 9 years, I still 5G is not deployed in our country, but testing is going on, and it's really good for me at least, or good for us. My proposal is the documentary policy documents for the UK government and other government. This is just reminded to you to share the session on. Oh, okay, yeah, just a minute. Thank you. So I can stop this. Just a minute. Yes. So I'm just opening my going to open my mail ID, and I will provide the 3GPP. I will just a minute. I'm just finding out the 3GPP PDF so that I can show you people. Otherwise, I'm just searching here. GPP or delete. So what I can do, I will send the latest release to organizers, because or either kindly send the mail to me. I will send the details, and if there any types of problems you people have, I will also do this. So I'm going to share screen. So here the release of 3GPP, the mobile broadband standards. You can see now 2024 up to release 18 are already there. So please kindly follow this release 18 or 17 is also okay for the current research. So just kindly just type the 3GPP release and you can get the link here, release 3GPP, right? So if you want to find out the release 18, I will send the PDF also. Advanced 5G RAN is there. So here, big documents are there. So you can able to sometimes in the PDF form, so PPT form, sometimes in PDF form. So this is always referred to PDF form because that they have the better details. So what is the name of this students? I will send the 3GPP license to you today. So kindly mail to me. I will send 3GPP and ITUT latest release to you today. Kindly mail to me. So this is from my side. Is there any other questions? Please let me know. Or shall I stop? Anyone is there from organization side?
Yes, sir.
Yeah. So this is from my side. Is there any other formalities? Tell me.
No. Thank you, sir.
Thank
So
you.
now, sir, thank you, sir, for such a nice session.
Thank
Now
you.
we will go for a lunch break. We will again rejoin at 1:50 p.m. So dear participants, today we are having one MCQ also. So all are requested to stay connected for the sessions so that all of you can appear in the MCQ at time. Thank you, everyone. Yes,
Sir,
sir.
may I leave? May I leave?
Yes, sir, you can leave, sir.
Okay. Thank you.
Thank you, sir. Good afternoon, everyone. Good afternoon, Koda sir.
Hi, good afternoon, everyone.
So now it's time for hands-on session. Dr. Konda Reddy Mopuri sir will take the hands-on today. It's hands-on 4. Sir, I made you the presenter.
Okay. All right. So just to recap, we started with understanding what is an artificial neuron, which is we have seen a couple of examples: MP neuron, Michael-Lewis neuron, and then perceptron. And we understood what perceptron can do. Essentially, it can do linear classification, right? And we also looked at the learning algorithm for perceptron. That means how to learn the suitable weights in order to classify the training data set with close to zero error. Right? This is the algorithm. Start with all zero vector, and then sample by sample you go on presenting. And whenever there is a misclassification, you need to adjust the weights according to this equation. And we also see what is the meaning of this update. Right? Essentially, we are trying to rotate the vector in order to include that misclassified sample. Let us say this is our W at the time t, and then if you are misclassifying one of these orange dots, you just need to rotate it. So adding this sample along with the adding or subtracting, essentially you are doing yi times xi, right? If yi is +1, you are adding. If yi is -1, you are subtracting. So what that means is essentially rotating the vector in order to inculcate the misclassified sample correctly. All right, let's see. So let's try to implement this algorithm. It's a simple algorithm in PyTorch. So in the slides, you have the link for this collab notebook. In any case, I'll give you the link in the chat box now so that everybody can access it. All right. So if you have the link already, you can open it. Otherwise, I'll do it now. To all the attendees, yeah. So I've given you the link for this notebook. I'll explain you how we can implement this simple algorithm, and there will be time also. I'll give you to basically try it on your own data, or the same thing. You can also run it, right? All right. So PyTorch is a library. Implement you will have a lot of functionalities for machine learning and deep learning. So you don't need to be afraid of this new library. It's a very friendly library. We can all use it easily. A lot of documentation is there also. So I kind of assume a little bit of Python experience. Even if it is not there, don't need to worry. Also, you can stop me whenever you feel like stopping me. Okay, so you can raise hand. Probably one of the organizers can kindly help us if there is any hand raising. Can unmute them and let them speak. Okay, all right. Let's get started with the algorithm. So by the way, this is called a collab notebook. It's a facility provided by Google. So what it means is you can try out and develop codes using the cloud facilities from Google. You don't need to have any hardware, no installations, nothing. You need to have internet. And once you go to collab.research.google.com, you can open a new IPython notebook and then start implementing your own model, code, anything. So it has a very rich environment. All these libraries are there. You just need to import them, right? PyTorch, TensorFlow, NumPy, anything. It's like a very rich environment. So it has some limitations. So memory you can use and the devices you can use is limited. But for our purposes, it is more than sufficient, right? So that's why without installation hassles and all, let us try to use the Colab notebook. Right, I strongly encourage you to also use this even after this faculty development program. It's very useful. You can develop a lot of things easily without much of hardware. Only internet is what you require. All right. Okay, so the first block is a simple importing. I need PyTorch, so I'm importing PyTorch. I need NumPy also. This is also another Python library. Use it for machine learning and a lot of numerical operations. NumPy is basically, for arrays and tensor manipulation. All right, so matplotlib is basically for plotting the um, data and visualizing the data. All right, so now I need to create a classification data set. Remember that perceptron is a linear classifier. That means it can classify data belonging to two different classes, right? So it's a simple binary classification that we are looking at. So I'm creating data D1 and D2, which is from each Gaussian. You have two Gaussians here, mean 0, standard deviation 1, mean 3, standard deviation 1. So it's a two-dimensional data. So x1 and x2, two components will be there for each of the data. I'm sampling that components from this Gaussian. For example, blue class, you see, the mean is around 0, 0, right? X1 is 0 and Y1 is 0. So this is some random data I'm taking, simple data, just to make sure we understand classification. We need data, right? Training data. So this is what I'm doing. So this is only for creating data, sampling from Gaussians. So torch.normal or NumPy also gives ability to sample normal distribution, right? You can do that. So this is that part. And plotting. Plotting, you can use matplotlib's scatter, where scatter of x component and y component, you give all the x components and all the y components, it will scatter data like this. So because data belonging to one class is in blue and data belonging to another class is in orange, now we can see the data, visualize the data. So we need a classifier which separates these two data, classification data. So this is the problem. So it is always encouraged to visualize the data if it is possible, right? So before you even attempt learning, you need to understand the data. So as a human, you also have to understand what is how does data look like. It will help in many ways, right? How the data is distributed, what sort of models, what sort of techniques we can use to classify this data. So it all starts with going through the data. So if it is low dimensional, you can always go through the data, visualize the data by plotting, etc. If it is high dimensional data also, you can component wise, you can try to see how each component, for example, speech and images are very high dimensional, right? You cannot plot them in a simple 2D or 3D plot. In that case, you can go through the samples, or component wise, you can visualize, right? There are 100 components or 20 components. So you can see how each component is behaving, etc. So not only visualization, a lot of other techniques also are possible. So just keep in mind, better to have a look and understanding of the data before you proceed. All right. So now we plotted the data. So remember, so we need to absorb the bias into, absorb the bias into the W vector, so that W transpose X plus B simply becomes W transpose X, right? So this is from our discussion of perceptron. I am just recollecting the concept. So we can always do this W transpose X plus B, but if you absorb B into W, it can simply be W transpose X. Simple operational facility, right? So that is what I'm doing. Sorry, that is what I'm doing here. So adding extra dimension to W and X also. So simply I'm adding one dimension and filling it with 1. So the data X needs to be filled with 1, and the parameter W needs to be, so B goes into the W actually, right? For example, our data is 2-dimensional, right? Now, what is the dimension of W? Can somebody put in the chat box? What is the dimension of W? Our X is a 2-dimensional vector. I view the messages. One second. Has anybody typed in on X dimension? Right. So Abhiranjan says X dimension. Yeah. What is the dimension of X? X is dimensional 2 because we sampled data from 2D Gaussian, right? So now what will be the dimension of W? Sheena says 2. Remember, we augmented the dimension by 1. Why? Because we wanted to have W transpose X plus B as a single operation, W transpose X. Right? For that, we need to increment the dimension by 1. Right? So let me just go back, show you what happened. So we added an extra dimension to make this simply look like W transpose X. Otherwise, we need to do W transpose X plus B. So how do we do that? So make W0 equal to P. So that way your 2 dimensions will now become 3 dimensions. Now you add 1 to extra. So let me just tell you how it happens. So these are important. One second. So I hope you can see the whiteboard. Our data is x1, x2. So W will be W1 and W2. So if we do this way, we have to go W transpose X plus B, right? But in order to avoid this, we simply what we do, we'll add this vector by one component, right? Now our W becomes B, W1, W2, and our X becomes 1, X1, X2. So if you just multiply, if you have dot product between these two, it will now be just W transpose X, right? You don't need to have that B plus B because 1 times B is already added in this, right? X1 times X, W1 plus X2 times W2 plus 1 times B. So that is why it's a good practice to do this. Add 1 to data, and that way you can have 3-dimensional W instead of 2-dimensional W. Okay, I hope I convinced you what is happening here. Let me just go back again. Right. So that is exactly what is happening here. So I added 1 extra dimension to the data. Now I can go have a 3-dimensional vector for W. Okay, so now you can see W is initialized with all zeros, dots dot zeros of X dot size of 1. X is number of points 200 and dimensions is 3, right? 1 dimension we added extra from 2D. So that becomes 3. X dot size of 1 becomes 3. So you will have 3-dimensional vector as W. All right. Now, before we train, let's see how W looks like. Okay, all this code is basically plotting the graph. So this is the data. And before we started training, W is like this. Is it a correct classification? Clearly not, because on one side you should have one color, on the other side you should have the other color. But it is not like that, because all W is equal to all zeros. This is how it looks like. Right? Just wanted to show how before the training W is looking. All right, now it's time for training. Remember, what is the training procedure for perceptron? Take one sample at a time, see if it is correctly classifying. If it is correctly classifying, don't do anything. If it is wrongly classifying, add y times xi to W. That's it. So you go on doing this, and if you repeat it n number of times, you will see at one point in time, you don't see any misclassifications. Or misclassifications will be fixed to so many number of points. So once you see there is no reduction in the misclassifications, you can stop. So that is the criterion. So I'm just translating these 2 lines of algorithm into code. Start with all zeros and then repeat for all samples. Whenever there is a misclassification, update W. So this is exactly what we are doing here in this. So you can also see. So I'm defining a function. It's a Python construct. So train perceptron. What do we need as input? We need data, label, weights, and number of epochs. Right? So maximum number of epochs. You cannot, if it is linearly separable, yes, you can get 100% classification accuracy. Otherwise, if it is not linearly separable, for example, this is not linearly separable. There is no line which can separate with 100% accuracy, right? So in that case, you can try for maximum 100 epochs or so, or whenever your misclassifications is not changing much, so then you can stop the training algorithm. Okay. So for E in the number of epochs, what you do? So number of changes, you can start with 0. You can keep counting how many number of points are misclassified in epoch number 1, how many points are misclassified in epoch number 2, and so on. For every epoch, you can count what is the number of misclassifications. When this reaches the minimum number, that is when you learned, right? Okay. So now within each epoch, take one data point at a time and see if it is misclassified. So how do we do that? W times X is the prediction and YA is the ground truth, right? So if both of them have same symbol, it is correctly classified. If both of them have different symbols, that means class 1 predicted is +1 and ground truth is -1, or predicted is -1 and ground truth is +1. In that case, multiplication will be less than 0, and that is when you have to update. So simple W is equal to W plus Y times X. That's it. Because there is a misclassification, you are updating number of changes. How many times W is changed, or number of misclassifications. Both are same. Whenever there is misclassification, we are changing, right? So number of misclassifications are equal to number of changes we made to W. So that is how we are updating it. So one, when in particular epoch, if number of changes is equal to 0, that means all the samples are correctly classified. You can stop. You don't need to train, because we reached the linear classification with 100% accuracy. Or else, if this condition fails, the for loop runs for maximum number of epochs. So it will try for 50 or 100 or 200, whatever you mention, it will run for that many and it will stop, right? So once that is learned, you can print the W also. So this is where I am calling the function W is equal to train perceptron of all the data X, Y, and the initial all zeros W, and I'm giving only 5 epochs, because it's a simple data set, and I observed that within 5 epochs it is getting correctly classified, most of them. I just give 5. So it will print W also. So this is the components W1, W2, W3. All right. So let's see, after learning the W, how the data looks like. So this is how the data is looking after learning W. Yeah, it's not 100%, but it is very, very good classification of the blue versus orange. All right. So this is a very simple algorithm, iterating through the data points, epoch after epoch. Remember, epoch means when you present all the training data once, it's called one epoch. If you present all the training data one after another 2 times, it will be called 2 epochs of training. Generally, depending upon the data, depending upon the algorithm, you need to run for multiple epochs. Sometimes for neural networks and all, you need to run for 100, 200 epochs. If it is a difficult problem, slow learning, you have to run for longer epochs. On the other hand, if it is a simple problem, simple linear classification, and the data is very well separated, in that case, you can run for small number of epochs, because this is trial and error. You have to try multiple numbers and then see if the classification accuracy is improving or not. Also, you can have a validation set also, where you can monitor the performance of the validation, and whenever validation performance is good or the best, you can stop. Right? That is how you decide on the number of epochs or other hyperparameters. All right. So let me just take you through the algorithm one more time, so that you get the implementation or the different aspects of perceptron. So simply, whatever is required, you import and then create the data. So this, you can take an example data, real data also, right? For this problem, I'm simply taking some random data. It's not natural data. I am creating the data where 2-dimensional Gaussians I'm sampling. 2 components are there. So 2D, it's a simple 2-dimensional data just for visualization, because it is easy to visualize 2D data. Okay. So this is how I'm visualizing. D1 is for one class, D2 is for other class. So how do I create the labels? So this is how I create the labels. So yeah, so for one class label is 1, for other class label is -1, right? So simply what I'm doing is basically taking 200 points, and then even I'm taking 1, and odd I am taking -1. That means 100 points for one class and 100 points for other class. Okay, so this is a simple way of creating a very simple toy data, you can say. But if you are importing actual data, you have to appropriately, make sure the labels are correctly given +1 and -1, and the data is also correctly read. Okay, now coming to the perceptron part. So if the data is 2-dimensional, you need to have W with 3 dimensions, right? You need to augment 1 also in X. So that is what is happening here. So I added extra dimension also. You can see here. So if there are 200 points, I'm adding d1 dot size of 1 plus 1. So initially it was 2, and then I'm making it 3. And the third dimension, I'm making it fill_1. So it is filling the data, all the tensor with 1, right? So this is also PyTorch construct. So I'll also try to give you very basic information about the PyTorch tensors. Just 2-3 minutes after this, I'll get there. All right, so once you have the W properly initialized and then X properly read, you can also plot before you go for training. This is what my W looked like. It's not doing the classification performance because we are not trained, right? It's a simple all 0 W. All right, now the actual implementation perceptron training algorithm. So those 2 lines, I've just made it into Python code. That's it, nothing more. Okay. So yeah, so general training looks like this. The neural network training, generally, you will have number of epochs, one for loop for epochs and another for loop for iterations. So let me differentiate. Epoch is for completing all the training data, right? Now, within one epoch, you have to take every sample and then present it to the training algorithm, right? That is called iteration. So I here is showing one data sample at a time. E here is one time if you completely show the training data, that is called epoch, right? So this you will see more and more in neural networks. You will have one for loop for epochs, another for loop for iterations, and within the second for loop you will have the model training procedure. So whatever is the update equation, you have to implement it in this for loop, right? There has to be a stopping criterion, whether it is validation accuracy, or in this case it is number of changes or number of misclassifications, right? Or if you simply say maximum number of epochs is only so much, after that many epochs, algorithm will automatically stop. Okay, so this is how I implement. So other parts are basic Python constructs, right? Defining a function, implementing a for loop, and then it's a simple mathematical operation and a print statement, appropriately arranged. That's what this. All right, so now I'm calling the training algorithm because this is a function call. This is a function definition. I'm making the function call here, train_perceptron with all the training data, labels, W, and the number of maximum epochs. After that, I'm printing my W. Initially, I started with all zeros. Now it is -5.3, -3.9, and 9. So now I can also plot how the classification is happening, how the W is separated. Right? All right. So do you have any questions here? All right. So if you are worried about PyTorch, so I'll simply present what I'll give time for you to take a look at the code and implement also. But before that, let me just take you through a simple. Right. So what is a tensor, or what is the quantity we use for processing the data in this typical machine learning and deep learning setup? Okay, So basically, it's a generalized matrix. So we know array means zero-dimensional tensor is scalar, and one-dimensional tensor is called a vector or array. Two-dimensional array is matrix because you will have a two-dimensional look to it. So it is also an array. Generally, we call it array, two-dimensional array, right? So that's called a matrix. If your tensor has, if your data has 3 dimensions, you will have a 3D tensor and 4D tensor, etc. For example, this is a 1D tensor, or it's a vector. Simply, it's a one-dimensional signal you can think of, right? So you have a 2D. Let's say you have a grayscale matrix. The data looks like this. It will have a matrix type of a appearance, right? So it is called a 2D tensor. When you have RGB sort of image where you have 3 different planes where you will have something like this, right? This is called a 3D array. You can have an RGB example. But RGB image is an example of 3D array. What about 4D array? Somebody is also saying, yeah, a video which has RGB frames, right? This is one video frame, second video frame, third video frame, and so on. If you have 1 second video, you may generally have 30 such frames. That means 30 is the 4th dimension, and the 3 dimensions are other dimensions are RGB planes, right? So this is a 4-dimensional array. That way you will have more and more such things. As the dimension grows, you will have 5D tensor, 6D tensor, and so on, right? So tensor is basically a generalized matrix from a scalar. Scalar is a 0-dimensional tensor. Vector is a 1-dimensional tensor, 2D, 3D, and so on. 5D tensor example, you can think of video is a 4D. Think of any what can be a 5D tensor. Let's say you have a mini batch of video frames, right? 1 video frame, 2 video frames, 3 video frames, 4 video frames, right? So this, yeah, it is still a 4D tensor, right? Right. Yeah, I don't have an example on top of my mind. So if there is any such signal you're processing where you have 5 such dimensions of variability, that makes a 5D tensor. All right. Okay. So it seems there are some questions. Let me just see if there are. Yeah, 3D is a video. 3D is a frame. 4D is a video. Let me say 4D tensor stacked. Yeah. 5D is 4D tensor stacked. That's right. But if there is any particular signal, nothing comes to my mind. All right. So there is another question. Abhiranjan Singh says, label data dimension in code understanding, sir. Labeled data dimension. Abhiranjan ji, can you please make, can you speak about it? So are you able to unmute yourself? You want to see the syntax for the label data dimension, is it? No, I'm not able to understand what you're saying, but let me take you to the code. Probably that can help you. Can somebody unmute Abhiranjan? Hello.
Good afternoon, sir. Good afternoon, sir.
Yeah, very good afternoon. Yeah, please go on. What is your question?
Sir, very little, sir. The dimension, how we are defining the x colon, sir, the dimension of the label data. how it is adding one more dimension, means x, y, and z dimensions, sir, and also the syntax of this, how this is a syntax x bracket colon 2 comma colon 2 is equal to d1. So
Okay,
from, and in the next it is from 1 colon 2. So how this is different, sir? Means first one is the row, sir. Before comma a comma b syntax is for first one is for row and second one for column, sir. But it is here for row 1 colon 2, and in the first one it is colon 2 comma colon 2, sir. So
okay. So this is basically all the rows with skip 2, right? Starting from 0. This means all the rows with skipping 1. I mean, with frequency 2, it's like subsampling basically, right? So if you just give one semicolon, it means all, right? But instead, if you give 2 semicolons and mention 2, that means starting from 0, I'm taking every second, 0, 2, 4, 6, and so on, right? That is what it means. This means starting from 1, I'm taking 1, 3, 5, 7, 9, and so on. So what the meaning of the syntax is that.
and
Okay.
in the second column for column, sir, a comma b, sir. So for column we are taking all
Up to the
column.
second. Up to the second. So what is that when I say so let me just write it here.
Means
So
x has dimensions, sir.
when I say this, what is this? All the values up to the second, 0, 1, right?
Yes, sir.
So that is what is happening here. So if I write this, all the rows, but only the 0 and first column.
0
Right?
and first column. Yes, sir.
Correct. So this is the same meaning here, 0 and first column here.
Oh,
But
yes.
here in the first column, what I mean, so if I write this, what it means is starting from 0, take every second 0, 2, 4, 6, 8, and so on. If I write 5 here, 0, 5, 10, 15, and so on. So
Yes,
that is
sir.
the meaning of this.
Yes,
Okay.
sir.
Basically, what
Yes,
I'm
sir.
doing, all the even samples I'm making class 1, all the odd samples I'm making class 2. That's it, nothing
Yes, sir.
more. So I'm just copying D1 into the even data. Right, D2 into the odd data. It's a Python syntax basically.
Yes, sir. Yes, thank you, sir. Sir, one more. The previous one, the x torch equal x torch dot empty 200 comma d1 dot size bracket 1 plus 1 dot fill 1. So here, sir, means it will create the torch is syntax dot empty means 200 the row, and the
Right.
column will be the size d1 size. So why
Yes.
this is 1, sir? Size 1 bracket in 1 plus 1, sir.
Right. So basically, D1 dot size 1 will give how many rows are there and how many columns are there. If I am asking for 1, it will give columns, right? So
Yes, sir.
I'll take you there. Just bear with me for 2 more minutes. I'll explain all this.
Thank you, sir.
Okay.
Yes, sir. Thank you, sir. Thank you, sir.
So yeah, so everything in PyTorch is a tensor. Whether it is a data, whether it is a parameter W, everything is a tensor. Okay, you initialize everything as a tensor. So tensor means, as I said, it's a generalized matrix. It can be 1D vector, 2D matrix, 3D cube, anything. Everything is a tensor. Okay, you have to use the tensor data type, right? So tensor is used for, as I said, encoding the signal or internal states and model parameters. Everything is in this PyTorch is tensor. Okay, so I'll tell you. So manipulating through these tensors is useful because the hardware, for example, GPUs and all, can use this structure to maximize the performance. So that is going internal, how the implementation of multiplication, matrix vector multiplication happens and all. So let's not go there, but remember that using in tensors help us get in the speed and the performance of the hardware. So that is why PyTorch, it makes you to initialize everything as a tensor so that operations can be executed faster and computations can be done effectively. Okay. So as I said, tensor can be, you can locate it in GPU or CPU, whatever. If you have the GPU, better to move it to GPU and compute in GPU so that things are faster there. Right. All right. So I'll show you how the tensors are generally worked with. Okay. So this is how a tensor can be defined. So I'm starting with tensor.empty of 3, 4. That means A is a tensor of 3 rows and 4 columns. If I just print a dot size, it will give 3, 4. So Abranjan, if I give 1 here, it will give 4. If I give 0 here, it will give 3. That means the 0th size, I mean first dimension and the second dimension, right? Because everything starts with a 0. 0 means first and 1 means second dimension. Remember, that is why we were using size of 1 here. That means D1 second dimension I want, because I want to increment that dimension by 1, right? Because I want to add quantity 1, so that W transpose X plus B will become only W transpose B. Sorry, W transpose X. So that is why I was using D1 size of 1. All right. So size is a function which will give us the dimensions of the tensor. So here 3, 4 is the dimension. So that is why torch dot size of 3, 4. Okay, that is why it is printing. All right. So there is another function, fill underscore. What it does, if you want to give a predefined value to all the elements in the tensor, you have to use fill. So I was using that also because I was filling that particular with 1 value, right? So here, if you see a dot fill underscore of 3.14 will fill 3.14 in all 3 into 4, 12 elements of A. All right. So you can perform a dot mean, a dot mode, a dot max, a dot min, all that things. So it will do the mean value, minimum value, maximum value, all that you can directly call. All right. This is a good thing about tensor. Also, you can access individual elements like this, a of 1, 2, a of 2, 3, or a of 1. So for example, yeah, the general syntax of Python hold here also. Okay, if you want to access the first row, you can simply say all here and then give yeah, all means semicolon, right? That thing works. So you can even slice. You want to take some subset of this range. For example, you want to take the first 2 columns. You can take using something like this. So you want to take all the rows up to the second, right? All the rows up to the second column. These things are all valid syntaxes, right? So it's nothing different from NP array in usage, but it will maximize the performance using the hardware, right? Right. So again, you can have the standard deviation, sum, and sum dot item. Yeah, everything, even the output of these commands is a tensor, right? So that is one thing you need to understand. So this is like a data type. Tensor is a data type, right? So you cannot add tensor to a non-tensor, right? If you want to make this a non-tensor, you have to use the dot item. Okay, so basically this is also a simple syntax you need to keep in mind. So otherwise, if you don't give dot item, what will happen is the data type of that will be a tensor. You cannot add to non-tensor values. So if I just use item, it will give 37.67, not tensor of 37.67. So this is the difference, right? It now becomes a Python scalar, like an NP or Python float value, you can say, right? So at times we have to use this dot item. I'll show where we have to use this also. Okay. Otherwise, by default, even the output of these operations is a tensor. You need to keep in mind. Okay. So that's about a simple initialization of tensor. So once you have that, next operation is basically we have W transpose X, right? That is the most used operation in most of the machine learning. So let's try to see how it happens. So dot product or summations or whatever operation you want to do, you can use like a Python operation. Right? For example, X and Y are 2 vectors or one-dimensional tensors, right? So you can see X, Y, it's a Hadamard product. That means in-place product, 1 times 2, 3 times 4, 5 times 6. It's not dot product. It's a Hadamard product. So in-place product also is an informal name they use for this thing. That's why 2, 12, and 30 is the answer. You can do exponentiation similarly to the Python. 2 stars means exponentiation, right? All squares. All right. So this is also another way of initializing a tensor. For example, if you want to specifically mention different values, like fill will give all the same values, right? That may be useful sometimes, but in most of the cases, you need to have different values, no? So this is how you can initialize. This is also possible. Toss dot tensor of whatever rows you want to have, you can give. All right. So MV is for matrix vector product. So M is my matrix, 3 by 3 is my M, right? V is so X is a 3-dimensional vector. You see here, X is 1, 3, 5, right? Now matrix dot MV of vector. So M is my matrix, M dot MV. MV means matrix vector product of giving X. So it will give the matrix vector product of M and X. Or you can use M at X also. M at the rate X means M vector and X, sorry, M matrix and X vector are multiplied together. Same, M dot MV is same as M at X. Right, this is another important, right? As I said, W transpose X is the most prominent operation. So we use either this or this. All right. So slicing is similar to NumPy, as I said. Yeah. So you can use A0, A1, or all the rows up to or from third column. Anything, whatever you use in general Python, you can use it. For example, here I'm using all rows from third column. That means I'm neglecting 0, 1, 2. Right? So 0, 1, 2 is missing. So 6, 4, 2, 2 will be the answer. 6, 4, 2, 2. Right? So these are all common operations that may use that may be useful. This also. So all rows from first column to the third column. That means 1 and 2 you will have. You're making them into -1. So all those values will become -1 because you are keeping all the rows and 1, 2, 3 columns as -1. So 2 rows are there, 1, 2, 3. Right. So these are all simple operations. Okay, I suggest you to take a look at this also later, or even whenever you require. So I'll share the link to this, or in the slides it is anyway there. Right, somebody asked it, I have not seen it. Yeah, so you can, I shared the link to this Tensor Basics notebook in the chat box. Please have just have it open, so in case the chat is closed before you copy it, you don't lose it. Or towards the end of the slides that I shared, you have the link also. Okay, the last slide has the link to that. All right, there are other small operations on tensors explained in this notebook. Please have a look at it. It's all simple operations, except that you try out, you don't remember, right? Otherwise, this is nothing great about tensors. All right, cool. So perceptron algorithm is this. I hope you understood the perceptron algorithm theoretically and then the implementation also. So keep this as a reference. Don't try to copy paste. You try to implement on your own. But as and when you fail or you try to, you need some help, then use this notebook that I shared with you, right? So now it's 2:35. Okay, let's take a quick 5 minutes break. What I'll do is start with other hands-on, which is gradient descent. Gradient descent is required for understanding training MLP. We haven't covered training MLP in our theory session. I'll try to spend some time before we actually code it. Okay, so this is not the focus of our module. That's why I am not giving time for you to code it right now. Okay, so please have it at your leisure time later. Once you finish this module, you can do it. Okay, so let's meet again at 2:40. I'll continue from wherever we have left. For example, where did we leave actually? So we were trying about 1 second. I think somewhere in MLP we were there. Right, so this is where, yeah, I'll continue from here. Okay, but while we have the break up to 2:40, if you have any questions, you can raise, and we can anything about the code that we have just discussed, or about perceptron, or whatever. Yeah, whatever I have covered. Any questions are there, I can take it up. I'm looking at the chat box. If you have any questions, you can post there. Can you zoom it? Yes, yes. I'll zoom it next time onwards. Yeah. Please, Lakshmi. Yes, please go on.
Sir, I have a question. Sir, we are using NumPy also for array manipulation and like dealing with arrays. So even this PyTorch has using PyTorch, we can deal with tensors. Tensors are also kind of arrays only.
Correct.
So what is the difference between those two? Is it because the time consumption is less when we use tensors and it is more when you use NumPy? Is it like that?
Absolutely, yes. The tensors are designed to make use of the hardware and optimize the operations, speed, and efficiency. That's right. So NumPy wasn't designed that way. Although the
Then why did they make NumPy? I mean, just a thought, like if we can do everything with tensors, why did they introduce NumPy?
NumPy was old actually. When NumPy came up, I think these GPUs, huge data processing wasn't there. Huge data processing and deep learning happened recently. Accordingly, tensors, Python, PyTorch, and all happened now. So NumPy is very old.
Okay, so to deal with simple calculations, we can go with NumPy, and if it is very huge arrays, then we can go with PyTorch
So
tensors.
more specifically, yeah, correct. You are right. More specifically, if you have bigger problems and you want to use GPUs, then it's always preferred. So although you may be able to implement in NumPy, but it cannot speed up and maximize the hardware utilization. Yeah,
Okay, thank you, sir.
no problem. Yeah, so let me remind you that so these most of machine learning, not only deep learning, is only it's a practical thing. Unless we practice by taking example data sets and coding them, so the learning would be incomplete, I would say. So it's not to frighten you, but this is the nature of the module is like that. Okay, so I strongly recommend whatever learning algorithms you have learned, be it regression, linear regression, logistic regression, or decision tree, SVM, perceptron, MLP, whatever. Unless you actually sit down and code them, and whatever you learned during theory, you just implement in some sort of program, it's not complete. Okay, so please keep that in mind and encourage yourself to choose a platform and finish coding of all the modules. And there is a lot of help also online. Okay, so please do that. Otherwise, it's not complete. Abhiranjanji, it is shared with the EICT people. The slides will be shared with you. I think they have already shared with you. If not, they will share. Perfect. So let's just continue. The break time is over. Right. Remember, we said perceptron is learning a linear classification, and we said it's only limited because a lot of real-world problems are non-linear. That means classification separation is not linear. Instead, it is a non-linear boundary. Also, complex boundaries have to be learned in order to classify the practical data. Right? We have seen a simple XR data also. Line wasn't sufficient to separate class 1 from class 2. Right? So that is where we look for more sophisticated classification. Okay, so this is what a linear classifier looked like: W transpose X plus B, and then there is a non-linearity, right? And we can extend this to multiple layers, multiple dimensions also. How? This is how one neuron looks like. Neuron and perceptron are interchangeable. Okay, when I say neuron, it is perceptron. All right, so you have this one neuron which gives scalar output. If I want to have multiple such outputs, I can have multiple neurons. That means W for this neuron and W for this neuron are different, right? If they are same, you will see the same value. That's useless, right? It is just copying the same value. So if you have multiple output, each of them will have different W's and B associated with them. And what is the purpose? It is learning multi-dimensional output, right? Not every output is scalar, right? Sometimes the output may be vector. So in that case, you need to have as many neurons in the output layer as your dimension of the output. So this is how we extend the linear classifier to multiple dimensions. What we did, we just had that many neurons as the number of output dimension. Each of them are different neurons. That means W's and B's belonging to each of them are different. So that is how we realize multi-dimensional output. So let us say if I make the output of the first layer input to the second layer, this will become, multi-layer network of perceptrons, right? We started with one neuron, and then we made more neurons within the same layer. And then we added another layer where we take the output of the first layer as the input to the second layer, and so on. So this is what happens in multi-layered network of perceptrons. So the name itself is very suggestive. It has multiple layers. It is a network of perceptrons. So that is called multi-layer network of perceptrons. So this is how it looks like. So the first layer will have a W1 and B1. And W1, B1, you remember, this is a matrix and this is a vector. Because within this layer also, you have multiple neurons. Remember, there are 6 neurons. That means you need to have 6 W's and 6 B's. All of it is captured by W superscript 1. That means there are 6 vectors here and 6 biases here, and so on, right? So from now on in MLP, whenever there is a W, you need to understand that it is a matrix, not a vector. Remember, in case of one perceptron, it is a vector, but here it is a matrix. Because you will have multiple neurons in the same layer, you make all the individual W's one row after another, it becomes a matrix, right? So that is why whenever in the scenario of MLP, if you see W, it is a matrix. Okay, so I hope it is clear. So that is how MLP looks like. So starting from one perceptron, we made more neurons, more perceptrons within the same layer, and then layer after layer, we added multiple layers. Simple. It's just a modular process. Okay, so everywhere we have a sigma, right? Whenever there is a perceptron, we have a sigma. What is the significance of this sigma? So sigma is non-linearity. So examples are tan h, hyperbolic tangent, or ReLU. ReLU means it looks like this. So when x is equal to, when x less than 0, output is 0. When x is positive, it will have a ramp, y is equal to x. So this is also a non-linearity. People use it more often. And the sigmoid function is also very familiar to us, right? 1 by 1 plus e power minus x sigmoid function. So these are all familiar non-linearity functions. They are called activation functions. Immediately after you perform W transpose X plus B, you need to pass through the non-linearity. You need to apply the non-linearity, right? Why? What is that? What is the reason? Remember, we've seen linear function of a linear function is still a linear function. So we said linear functions are limited in capacity. We need non-linear boundaries. That is why we are introducing non-linearities between two linear operations. Is it clear? This is a very important question. What is the significance of non-linearity in MLPs or in general neural networks? Because if we don't have the non-linearity, linear function of a linear function, let us say first layer is one function, second layer is another function, right? At the output, what you see? Second layer of first layer of input, right? Let me just take you to the, just 1 second. So this is an important thing we need to understand. Right. Right. So let's say F is my first layer. So this is my input. F is my second layer. Oh, sorry. This is hidden first, I will say. Yeah. So G is my second layer. This is my output. So how do we write? Output is equal to G of H1. What is H1? F of input. Right? So clearly, this is one function and this is second function. Second function of first function, right? If both of them are linear, both of them can be simply replaced by one linear function, O of output, right? G of f. If both of them are linear function of a linear function is still a linear function, and linear function of input is limited. We say this is simply perceptron and it cannot do non-linear classification, right? It cannot do non-linear classification. That's why we don't want this to happen. So how to avoid that? Introduce a non-linearity after f. So if you use if you introduce a non-linearity here after the first function, it cannot degenerate into a linear function, right? So I gave an example also in last class. If you remember, 2x plus 3 is 1 and x minus 5 is another one. So let's say this is f and this is g. What is f of g? It will be 2x minus 7, right? It is still a linear function. F of g of x is still a linear function because it's a linear function. This is also a linear function. Linear of linear is still a linear. We don't want that. We want non-linearity. Only then we will be able to separate non-linearly separated data. So that is the importance and significance of non-linearity. After every W transpose X plus B operation, we will have a non-linearity, either a ReLU or hypertangent or sigmoid or anything like that. All right, so that is how we construct an MLP. MLP is, you can think of a simple neural network. So whenever you say neural network, most likely it is MLP. There are other configurations also, convolutional neural network, recurrent neural network, etc., etc. But in general, you see, MLP is simply referred to as neural network also. All right. So there is a lot of theory also developed behind this MLP and neural network configurations. So what is it? So I'll simply state the theory without going much into the details and proofs of something like that. So what it says is we can approximate any function f from a to b onto a real line R with a linear combination of ReLU functions. So this is called universal approximation theorem. So what it means is any function can be learned in a rude way, in a very crude terms. Any function can be approximated with a linear combination of ReLU functions. So how does a ReLU look like? This. Let us say I'll give a simple function x cubed plus x squared minus x minus 1. So this is clearly a nonlinear function, right? It has a lot of nonlinearity behavior. So I say any such function can be approximated by linear combination of these guys, ReLUs. It looks a bit surprising, but it is true. So let me show you how we do that. So if you see, these are 3 ReLU functions. So ReLU is so let me, this is ReLU, right? So you can manipulate this guy. You can add a bias, subtract a bias, multiply x, and that way you can flip around y-axis. Everything, whatever you want to do, you can do, right? Having a positive offset, negative offset, or having a negative coefficient multiplied to this ramp function, everything and anything. So if you do those manipulations, you will get for every different manipulation, you will get a different function, piecewise linear function. So you just do, for example, I'll have, there is a question, just 1 second. We can deal with nonlinear separable function with MLP, is it? Yes, we can deal with that, correct. So Mr. Vijay, yeah, that's what we are discussing. MLPs are capable of handling non-linearly separable data. How? By having non-linearities between layers and having multiple layers. Clear? Okay, right. So I'm showing an example. I want to learn a function which is x cubed minus x cubed. Let me just go back. What is the exact function? Plus x squared minus x minus 1. Okay. So how do I learn that? Having only ReLUs. So let us say I have 6 ReLUs. First ReLU is minus 5x minus 7.7 and so on. So you can even plot this and see. Okay. So I define 6 such ReLU functions with so what is in between? Sorry, what is in the parenthesis? It's a simply W transpose X plus B, right? W is minus 5, X is X, and B is minus 7.7, right? Here also, W is minus 1.2, B is minus 1.3, 1.2, 1, 1.2 minus 0.2, and so on. Essentially, I have 6 perceptrons with different W's and P's, right? Operating on a scalar X, right? So if I have such neurons or perceptrons and I combine them in this fashion, -1 times the first neuron, -1 times the second neuron, -1 times the third neuron, and so on. 1 time fourth neuron, 1 time fifth neuron, 1 time sixth neuron. If I just do this multiplication uh, and addition, it's a linear combination of all these 6 neurons. So this is how it looks like. The red line, the red curve, which is very, very closely approximating the nonlinear function. Remember, ReLUs are piecewise linear only, but thanks to these biases and the offsets, right? So the multiplicative W's and the biases, you can manipulate in such a way when you take the linear combination of these perceptrons, you can closely approximate. You can even go further if you add more and more such perceptrons. You can make the error close to 0. Okay, so this is one demonstration. Actually, it's the approximation theorem is even more powerful, right? So again, let's revisit the statement. We can approximate any function f from a closed boundary a to b to a real line r with a linear combination of not only ReLU, in fact, any nonlinearity with mild assumptions. Okay, so in practice, we whatever we use, most of these sigmoid, tanh, ReLU, all of them hold these assumptions. That's why, so we simply say one layer of what is this actually? So these are 6 neurons, right? 6 neurons means only one layer and 6 different neurons in that layer, right? So theoretically, any function can be learned with one hidden layer, taking the linear combination of these perceptron outputs, right? But there are a lot of aspects to this. So for example, going into a deeper understanding, this is how it looks like. So W is a matrix, you're applying on X, and B is a vector. So you have nonlinearity and you're taking a linear combination. So this W is not the actual parameters. So this is -1, -1, -1, +1, +1, +1, right? That W is sitting here, taking a linear combination of all these perceptrons. Okay, so what it looks like is this. So this is one layer. You have 6 in this particular example. You have 6 perceptrons, right? And this is a linear combination: -1, -1, -1, +1, +1, +1. So it can be different also. You have to understand that linear combination means any A F1, B F2, C F3, and so on, right? A, B, C can be different. All right. So that is what universal approximation theorem says. So better approximation requires larger hidden layer. As I said, if you increase more number of perceptrons, you can get close to 0 errors. But the theorem doesn't say how they are related. So the approximation error and for example, number of neurons in one layer, or how many layers can we go on. So what it boils down to is basically, theoretically, it is possible to have one neuron, one layer itself to realize any function, but it may complicate. So it may need you to require add a lot of hidden units within the layer. Instead, people negotiate with depth actually. Okay, I cannot add a very huge number of neurons in the first layer itself. What I'll do is I'll add small number, rather I'll add more and more layers. So that is another way of handling the complexity, right? Theoretically, it is possible to learn within one layer, but it may require you to add a huge number of neurons. So trade-off is going more deeper. Vijay asks how to optimize number of hidden layer in neural network. So that's a research problem. So we don't know also. So learning efficient neural networks is definitely an ongoing research. So network architecture search, simply NAS, is a very, very active research area. So there is no simple answer to that. So we know theoretically this much: one layer of hidden neurons is efficient or is sufficient to learn any function, but it doesn't say how many. So that is where all the research is going on: how to decide number of layers, and within the number of layers also how many neurons, right? I hope answered your question. So there is no straight answer to that. Theory says you can realize any function with one layer, but it doesn't say how many number of neurons you should add. So we need to find out problem to problem, data set to data set, based on the complexity, it varies. And sometimes architecture of the configuration means CNN or MLP, so that also matters. All right. You're fine, Vijay? All right. So if you are asking about how to train, I'll come to that. So about the number, yes, it is. There is no simple answer. We have to. It's a heuristics, trial and error. And if you get more and more experience, you will understand. You will get some good estimates. For example, if you work on multiple problems and experience how each problem behaves, you will have a good idea about choosing the number of layers and size of each layer, etc. For now, for beginners, it's a tough job. There is no such mantra to just give. All right. All right. So this is fine. So now we understand MLP, how it looks like. This looks like, yeah, this is how MLP looks like. And what it has is, it has enhanced capability. So clearly, any function, linear, nonlinear, difficult, easy, doesn't matter. Any function can be learned with a linear combination of multiple neurons. So that is our power. Now we know we have theory behind these configurations. So with that, we go for implementation. So how to actually learn these W's and P's? We know it is sufficient, but as I said, it doesn't say much about the number of neurons also, how many to have within that, etc., etc. So these are all still developing, and as I said, no clear answer can be given, but you can try out different configurations and find out which suits you. Okay, there are some things you can do to avoid mistakes and be confident about your model. So we can visit it later. Okay. All right. So how do we learn the weights and biases? That's the whole interest. So recollect all the machine learning tools that you have learned, starting from regression, linear regression, logistic regression, decision trees, or whatever. Yeah, SVMs, etc., etc. So there is a training procedure, how to come up with optimal W. So what is optimal? So how do we actually decide which W or what? How do we compare Ws? Which W is better if I give two Ws? Any answer? How do we prefer one W versus another W? Let's say I give training data for perceptron, linear classification. I give two Ws. Okay, W1 and W2. I'll ask you which W is better, which W you prefer. How do you answer this question? Exactly. Nikita Jain says that W which lowers the error. Correct. So you have the training data. So training data is representative. We need such a W which gives lowest error on the training data. So error, what is error? Error is discrepancy between predicted and ground truth. So this error function is very, very important in machine learning. So you need to come up with a suitable error function. So for classification, regression, based on the problem, you need to come up with a suitable error problem. So let me repeat, error means measure of discrepancy between the predicted value and the expected value. Let us say for class 1, we want the label 1 to be predicted. And on the other hand, if the W or the model predicts -1, there is an error. We have to quantify how much is the error, right? On the other hand, if it predicts the right value, we will say, yes, it is correctly predicting, there is no error. So that is how we need to measure. We need to compare different Ws, right? So gradient descent is one useful general technique that is used to update the model parameters, learn the model weights. Okay, so we will see how it is useful. All right. So as I said, this finding model parameters or training the model is basically minimizing the empirical risk. So empirical risk means, in a very crude terms, I'll try to explain. So you have the training data. Let us say for every training, for every problem, classification or regression, somebody gives you data, or you collect your own data, right? So the loss computed on that is called risk, or the loss incurred by the model, correct? So you have to optimize, means minimize the risk. So when you do as expected, your loss value is 0. When you don't do as expected, your loss value will be large, high, right? So optimization or training is our efforts to minimize that loss towards 0. So that is called empirical risk minimization, because empirically you are computing on the set of training data, how much is the loss, and slowly you are trying to minimize. Iteratively, you change the parameters in order to minimize the loss incurred on the training data. So the whole training process is called, that's why, empirical risk minimization. Okay. For example, you take a simple linear regression case. You have training data xn and yn, right? You have w and b. W transpose x plus b is your prediction, right? You have to compare with the ground truth yn. How do you compare? Mean squared error is one way. This is what is happening in this equation. So predicted minus ground truth whole squared. So this has to be squared on the outside actually. So f minus yn whole squared. And take the summation over all the training data. So this is one example of a loss function, which is a mean squared error function, right? So because you're taking mean on the squared error, that's why it's called MSE, mean squared error function. So this is one loss function. So if I give this and ask you what value of W and B will minimize this error, how do you proceed? So I clearly give you, this is the equation. So I give you x and y and values. Now I ask you to find out what is the value of W and B which minimize this equation, which minimize this loss value. Any ideas, any guesses how to go about it? All right, so we have to do a bit of calculus. So remember, we've done in +1, +2 level. There is an answer, I think. Let's see. Derivative, right? Derivative is the key. Yeah. So this is where we've done calculus, right? So maxima, minima, how to find maxima of a function, minima of a function, etc. Right? So let's say I'm drawing a function, a very simple function. So this is x, and this is my L of x, or some function of x. Okay, L of x. Okay, this can be any function. Generally, you will have something like this. Sorry, it has to be a function. Right. So that means, so this is called maximum. This is called minimum. Sorry, here in this case, this is the minimum. Right. This is the minimum. So if you think this is a loss function and this is w, not x, so w and b are the independent variables, right? So if you change w and b, the loss also changes. So that is what you should assume. So this can be w or b, and this can be w of L of w or L of b, right? So we need to find this location. What value of w will give us minimum loss value, or what value of b that gives us the minimum of loss value. So I'm just quoting from the calculus. So what we do at maxima or minima, derivative of the function becomes 0, right? So you see the tangent and slope of the tangent is equal to 0, right? So we do that. We compute the derivative with respect to these variables and make it equal to 0. Dou L by dou B, and then equal to 0. If you solve these equations, you will get the value of W, right? So I don't know whether linear regression is covered in this program or not. So if you just have Wx plus B is your predicted value y hat, right? So estimate of B hat will be something like, yeah, so W hat. I'm just giving you, if you do this, if you solve these equations, you will get expressions like this. Sigma of x minus x bar y minus y bar divided by sigma of x minus x bar squared, something like this. I might be wrong here. I'm just giving you. If I solve these equations, you will get something like this. Similarly, another expression for p, because if you remember, L is what? L is sigma I is equal to 1 to n w wxi plus b minus yi whole squared, right? So now I can compute dou L by dou W, dou L by dou B. So this simple quadratic equation, and then make it equal to 0. I'll get expressions for W and B, right? So this way we can find out if the loss function is very simple, and if you can analytically find out the expressions, this is well and good. But the problem is, in most of the cases, this is not the case. So the loss function is very convoluted and it's not very easy to find expressions for W and B, right? Think of an MLP. You will have, for every layer, you have a W matrix and B vector. If you have multiple layers, you will have that many Ws and Bs, right? So, and there is no simple, straightforward equation. You may try to get, but you need to bang your head against a wall, right? A lot of operations, one after another, happen, and you can't. Maybe it's not very feasible to apply this straight away, right? For example, what did we do in case of perceptron? We haven't done that, right? We have done some ad hoc recipe, some sort of a trick, right? We had W and we didn't do this derivative equal to 0. Instead, we did other way, where we went on rotating the linear separation whenever there is a misclassification, right? It may work for some cases, but in complex cases, what you do is gradient descent. So what is gradient descent? So whenever the loss minimization and analytical solutions for these variables is not possible, we adapt to gradient descent. So let me see what gradient is. What is the gradient? Gradient is a defined like this. For example, your function f is defined from RD to R. So meanwhile, if you have any questions, please stop me. I can explain. So I hope everybody is following what we are trying to do here. Okay. Yeah, I hope things are going fine. Okay. So what is gradient? Gradient is defined like this. If you have a function f defined from RD to R, that means mapping is from x to f of x, right? The gradient is defined like this from the output space. So basically, gradient is defined like this. Gradient of a function f with respect to x will be a d-dimensional quantity computed like this: dou f by dou x1, dou f by dou x2, and so on, dou f by dou xt, right? So if x is a two-dimensional vector and f is a scalar output, you will have a two-dimensional gradient. So just pay a little attention here. So my function is defined from 2D input to scalar. That means 1D output. Okay. So my gradient will have same dimensions as the input. Input is 2 dimensions, then my gradient will also have 2 dimensions. It's simply dou f by dou x1, dou f by dou x2, and so on, dou f by dou xt. If my d dimensions are there in the input, I'll have similar dimensions in the gradient also. So this is by definition gradient. It's a vector. It will have a direction. All right. So understanding gradient is very important to appreciate neural networks and deep learning. So please don't hesitate to stop me in case you have a doubt. Okay. So this is the crux. If you understand gradient descent and backpropagation, you understood every damn neural network out there. Okay. That's the magnitude of this concept. Okay. Okay, fine. My function is not a scalar function. For example, here it is a scalar function, right? What if my function is not a scalar, but instead it's giving a vector output? Same, you will have m components in the output, right? You compute gradient for each of these components. For example, that's what I'm doing. So for first component, you compute the gradient. Second component, compute the gradient. Everything is a vector, right? So make them look like a matrix. Then you will have the derivative of or gradient of that function, multidimensional function with respect to multidimensional input. So it looks like a matrix. So it's called a Jacobian, right? It's nothing but derivative only, except that because your output is a vector and input is also a vector, the gradient looks like a matrix. Every component of the output, you are computing the gradient vector and stacking them as rows. For example, you see the first component of f, the gradient is here. Second component, second row. Last component, last row. F1 to F1, Fm are m components of the output. All right, everybody is following. So this is the gradient, which is called Jacobian. Okay, if the function is multi-dimensional output, it's called Jacobian. Otherwise, it's called gradient. You will have a vector here. You will have a matrix here. That's the difference. That's the gradient. All right. Now, for minimizing a function, remember all the journey started from minimizing the loss function. Why? If we minimize the loss function, that means we are doing good. Our errors are less. The training data is very well learned by the model. So start with a definition of a loss function and try to minimize it. So that is our goal, right? Because the function was complex, we cannot simply do dou L by dou W is equal to 0 and get the equations for W and B. So that is why we are resorting to gradient descent. Okay. So for minimizing a function, gradient descent uses a local linear approximation. So remember in +1 and +2, we had this Taylor series expansion, right? About a point W0, I am approximating the loss function with a linear approximation. So within this closed neighborhood of W0, I am approximating the loss. That is why hat is there. My approximation of L surrounding W0 is like this. L of W0 plus the dot product between the gradient at W0 and the difference between W and W0. And some square term is also there. Let's say I am approximating like this. Okay. So remember, I always look for the W where loss is becoming 0 or close to 0. That is our aim. So if this is my approximation, what I'll do is I'll try to make the derivative and then make it equal to 0. Okay. Because now it is a linear function. So very simple approximation is there. I can go for finding the derivative and then make it equal to 0 and find that W within the surrounding of W0. Let us say we are standing at W0. I'll explain why we have to think like that. But let us say in the independent space, we are standing at W0, and within our surrounding, we are looking which point has minimum error, lower error. Okay, that is what it means in a crude sense. So I am now differentiating with respect to W. So this is a constant quantity. It becomes 0, and W has a multiplicative factor. So that only will reside, and W0 is again constant. So you will get 0. And here W is there, square term is there. So 2 times 2 gets cancelled. 1 by eta minus times W minus W0. So I'm just doing a simple derivative on the LHS and RHS. Okay. So this I now make it equal to 0. What will I get? I'll get W where the loss is very minimal within the neighborhood of W0. Okay. So again, I'm repeating. So I think I'm assuming that I am standing at W0 and I look all my surroundings for a W where my loss is becoming minimal or 0. I approximate within the neighborhood, the function follows this kind of an approximation. It's a linear approximation, although there is a square term, which is very minute. You have to think of that as the neighborhood is very close by. This value would be very small. That we are squaring it, right? That's why. So now I do that deriving and making it equal to 0 and then find the value of W. So make it equal to 0, LHS, and send all the terms that side. So it will become W0 minus eta times this guy, right? So when you stand at W0 and you have to move in this direction to minimize the error. So that is the gist of it, right? So you have to repeat this process again and again. You go to this location and now look around, make a linear approximation, find the derivative and make it equal to 0. Again, you will essentially do this, finding the derivative and going in that opposite direction. Okay, So this is what gradient descent means. So find gradient of the function and then go in the reverse direction, right? Why is that? Theoretically also, if you observe, gradient gives the direction in which function increases, right? So gradient is the direction in which function increases. But remember, we want to decrease the loss. We want to minimize the loss. So what do? We go in the opposite direction, correct? So that is what is happening. I'm standing at W0. I'm looking at derivative direction. I'm going in the negative direction because gradient gives the increment direction. I want decrement to happen. That's why I go in the opposite direction. By how much? By eta times. So I don't go very long strides. I'll take small steps. So eta is my step size. So this is a very crude and broad understanding of gradient descent. I approximate the loss function within the neighborhood as a simple linear function, and then I will compute the gradient and go in the direction of the negative gradient. Okay, so if you just want to understand what it means in diagram, so this is how it looks like. Let me clear this up. Right. Right. So if the function is very simple and very well behaved, it looks like this. Okay, this is W. And now this is L of W, loss computed at W. Okay, so let's say this is my W0. Okay, at W0, what is the function value? This. It can be, let's say, 10. Okay, and now I want to reach this minimum point. This is my goal. I don't know where it is. Okay, I just start from here. You have to imagine that you are only standing here. You don't know which direction the function is increasing, which direction the function is decreasing, nothing you know. Okay, so at this you can compute dou L by dou W. This gives the direction in which the function increases. Okay, so you have to, this is the vector. So clearly if you go in this direction for W, the function is increasing, right? If you go in this direction, on the other hand, the function is decreasing, right? So 10 becomes 11, 12, 13. On the other side, 10 becomes 9, 8, 7, and so on. So this direction, this is the gradient direction in the green. So I have to go in the reverse direction by small amount. So let's say I'll go by small amount here. This becomes my W1, which is equal to W0 minus eta times the dou L. Dou L, this is how gradient is generally represented. Okay, this eta is needs to be really big. Sorry. Yeah. So it can be 0.1, 0.2, some small number. Okay, without going in the strong strides, you have to go in the smaller steps. Okay, now I'll go to W1. W1, if we go, this is the value of function W1, which is 9 actually. And slowly, if you go there and compute the derivative again, which is in this direction, so in the opposite direction, go slowly, go all the way, you come here. Sorry. Okay, once you come here, this is the wanted point. This is the minimal value, loss value we can achieve, right? So what happens here? So generally, you don't go anywhere. If it is convex function where you have smooth and only local minima becomes the global minima kind of a situation, that means you won't have zigzags like this. Okay, you will have a very well. So I can give a definition of convex function also, but it's a little complicating. So just think of complex function as a very well-behaved function, right? So when you draw a line between two points, the function always lies below. But this, it is not the case, right? If I draw a line here, the function is going above the line also. So that is why it is not a convex function. So convex function means when you draw a line, the function always lies below the line. In this case, you can clearly reach a minima, which is the global minima. Global minima means the lowest value function can attain. For example, if you see the red function, which I have drawn here, this is a local minima, this is a local minima, but this is a global minima. That means So this guy is a global minimum. This is the lowest of the values, but this is a local minimum because within the surroundings it is the minimum value, right? Here also within the surroundings it is the local minimum, but if you take all over, this is the minimum. It's called global. The name is self-suggestive. This is local minimum, right? So in convex functions, both are same. Local minima is the global minima also. All right. So this is how you should imagine. You're starting from a W0, some random initialization of W's, and compute the gradient direction and go in the negative direction of the gradient. Slowly make progress towards the lowest cost. Okay. All right. Now imagine W is a scalar here, only one dimensions. So you need to understand all the machine learning problems we have is very high dimensional problems, right? So in our example of perceptron, W is the data is two-dimensional, right? But here data is one-dimensional. Now, if you go to higher and higher, complex problems like images, speech, video, language, you will have very high dimensional data. So all this happens in very, very high dimensions, right? 128 dimensions, 64 dimensions. We can't even imagine this kind of equivalent. All right. So, but you need to understand this is what is happening at a grand scale. So now your W's will be not one, you will have multiple. In a simple three-dimensional case, what will you have? You will have another W like this. This is W2, this is W1. Now imagine a so a volume or a point cloud in this space, 3D space. Now you have to go in 3D in order to understand the function value, how it is decreasing, etc. Okay, so the gradient also will become a 2D vector in that case, because you will have W1 and W2 two dimensions. Your gradient also is a 2D vector. Okay, so like that you have to understand. You have to imagine whenever gradient descent is happening. So from some starting point, you are making small progress towards the local minimum. Again, if you have any questions, stop me, else we'll proceed. All right, so all this is used in not only in neural networks, in general optimizations also gradient descent is used. It's a more general technique. So neural networks also use this, but think of this as a more powerful and general technique. All right.
Sir,
Sure.
sir, I have a question. Sir, what is the real time example for this gradient descent algorithm? I mean, so first one question. Audio signal is a three-dimensional signal, right?
Okay.
So look, I just want to know how to use this algorithm in a real-time application. Is it like useful, this one?
It is highly useful. So yeah, so this
Do
is
we use this in any example where in real-time application wherein we can use this? I just want to know how
okay, I
like
understand. So create a problem. You said you have a problem of classification audio, or what is the problem? Is it regression or classification?
suppose I want to classify audio like male and female, something like that.
Okay,
How do we use
perfect.
this one?
Right. So any machine learning problem, as I said, you will have a data, labeled data in this case, because this is supervised problem.
Supervised learning, yeah.
You need to come up with a loss function. So you need to have a comparison between the predicted and the ground truth value, right? Right. So think of a perceptron. So what you have learned a perceptron, right? You have seen
Yes,
the
sir.
code also. X is now your data. So for example, you have three-dimensional data representing each of the sample, right? So X would
Okay.
be 3 dimensions. The label would be +1 or -1. Let's say +1 for female and -1 for male. Okay. So now you can use this. So posing a problem is the first thing, right? So you have to understand it's a classification problem. My data is two classes, +1 for this, -1 for this. And then now you go for either perceptron or logistic regression, things like that. Okay. So once you have the loss function, okay, let me give an example of loss function also. So thanks for the problem. So let's say this is a two-class problem. So logistic regression is a classification algorithm where it's derived. I mean, it's motivated from linear regression. So Wx plus b is the linear regression, right? So my label is either +1 or -1.
Yes,
So
sir.
this is my loss function. So my W and B are parameters. I want to learn W and B. Now, how do I compare? Loss function is required. So I initialize the W and B with some random values, and now I go on learning them. Before I learn them, I need to understand how the values of W and B are doing, how much the error they are getting, right? So I need to come up with a measure. So let me go back again. So okay. So my problem is this: W transpose X plus B. If it gives +1, sorry. So this is a simple matrix, dot product and addition, right? So if it is positive, class 1, if it is negative, class 0, right? So let us say this is class 1 and this is class 2, something like that. So if, let us say, for a sample, I got predicted value as +1, whereas the ground truth value is -1. So this is a unwanted, undesired, right? But for one sample, ground truth is +1. My model also predicted. So let's say this is y hat. Y hat means predicted. So these are my predictions. These are y, ground truth. Okay. So this is an undesirable situation, isn't it? When the ground truth says -1, my model also should -1. Otherwise, there is an error. Okay, this also is an error. So let's say if it is +1, ground truth is +1, and this also +1, we are doing good. So no need to worry about the model. But
Means we wanted to predict it is a, suppose it is a female voice and we predicted it is a female. So that's what you want to say.
yes. So we need to quantify this. So we need to say the model that you are doing wrong. This is -1, but you are predicting +1. You have to convey that to the model. So that is where the loss function comes. Okay. How do we do that? Let us say I multiply yn, the ground truth value, with W transpose xn plus b. Okay. So I'm just giving you one way of creating the loss function. So if both of them have positive signs, I am good, right? -1,
Yes, sir.
it predicts -1. This is also good. +1, it predicts +1. This is also good. Either, so let's say my ground truth is +1, it gives -1. This is wrong, right?
Yes, sir.
So by looking at these values, I am intuitively coming up with this loss function. Okay, whenever both of them have same sign, I am good. Whenever both of them have negative signs, this is bad. Correct?
Yes, sir.
So I am now I'm defining my loss function like this. When both of them are um, same sign, this product will be positive, and this can be more positive value also. It can be 15.2, it can be -1.3. It need not be +1 and -1 also, because this is a real value, right? Wx plus b can be anything, -infinity to +infinity, right? So I know this can be any range between -infinity to +infinity. So what I'll do is I look at the sign. Okay, as long as the sign is positive, I am okay. As long as the sign is negative, I'm not doing good. Okay, so this is where the values can take -infinity to +infinity. So I apply some intelligence. So I know sigmoid function acts like this. From -infinity to +infinity, this is only compressing between 0 and 1, right? So this value is 1. I know sigmoid function can compress the range of -infinity to +infinity between 0 and 1. Okay, now I'll apply sigmoid on this. So this range becomes between 0 and 1, and clearly 0.5 is my point of interest. So all this is class 1, all this is class 2, right? So whenever the sigma output is lying in this range, this is male class and this is female class, 0.5 to 1. Okay, I need to again think of a way of quantifying it. What I mean to say is, so this is still a it's a monotonic function, right?
Mhm.
I'll try to make it even simpler. So when the positive value is there, our loss should be minimal, right? When the negative
Yes, sir.
value is there, loss should be high.
Maximum. Yeah.
Loss should be maximum. So what can I do on this to inflict this kind of a result? Okay,
Mhm.
so for values between 0.5 to 1, I need to have smaller value. For values between 0 to 0.5, I need to have bigger value, right?
Mhm.
Because this is a misclassification region, right? 0 to 0.5 is my misclassification region, and 0.5 to 1 is my safe region, because
Mhm.
product value in the positive region converts to +1 to plus.
Means we are talking about only one type of classification. In that we are assuming this.
Mm,
In the
okay.
sense, 0 to infinity is one class and 0 to minus infinity is another class. So
Yes.
you are telling 0 to infinity, in that we have two segments. So if it is from plus
No.
0.5 to something, it is proper classification. If it is 0 to 0.5, it is not a correct classification.
Yes. So in a way, what you said is correct. So the range is minus infinity to plus infinity. After
Mhm.
applying sigma, it became 0 to half, 0 to 1.
Yeah,
Okay.
yeah.
So within 0 to 1, so this prediction value between 0 to 0.5 is misclassification, and
Yeah,
0.5
yes.
to half is correct classification, right? So
Yeah, yeah.
because so so it's really difficult to explain how we came up with, but just try to understand
Yeah.
what happens
y-
if I apply
Okay.
log and then negative. Okay.
Okay, sir. Yeah.
So for the 0 to 1 value, as the values are closer to 0, so let us say everything in the log value is closer to 0. Log of 0 is close to infinity, right? Minus
Yes.
infinity. So minus times minus infinity is positive, plus infinity. Loss is very, very high when I have this value close to 0. Okay.
Mm.
On the other hand, if my value within this log is close to 1, what will happen? Log 1 is,
0.
that means I am not incurring any loss. My model is doing good. Zero loss means training error is 0.
Okay. Yeah,
Okay.
yeah. Yeah,
So
sir.
whenever my product of prediction and this is prediction and this is ground truth. Okay. So
Mhm.
both of them are very high positive value, I'll have 0 loss. When the product of this is negative, very high, that means misclassification is happening. So
Mm.
loss is defined like this. It will capture high value when misclassification is there. It will capture 0 value when correctly classified.
Correct classified. Okay.
Okay. So
Okay,
this
sir.
is some intelligent way of capturing this classification and misclassification. Okay.
Mhm.
So this is not the only way. You can come up with another mathematical operations which
Mhm.
take prediction and ground truth and come up with this desired behavior. Okay. We want to penalize these kind of predictions and encourage this kind of predictions, right?
Mhm.
So this the green ones we need to encourage, and these guys we need to penalize. So whatever equation that reflects this behavior can qualify to be a loss function.
Mhm. Okay,
Okay,
sir. Yeah.
now I have a loss function defined. Okay, now how do I apply gradient descent? Let's go to the slides. So this is my loss function. So I formulated a loss function to simply classify my audio signal into male versus female classes. Now how do I do? I'll compute the derivative, dou L by dou W, dou L by dou P. So this is a simple analytical formula. I can compute it, right? So before you compute, I want to give some more help also. Sigma is there, na? So dou by dou x of sigma is sigma times 1 minus sigma. So you can do the math, 1 by 1 plus e power minus x. So if you just compute the derivative with respect to x, it looks like this. Similarly, log of sigma x also you can compute. Derivative of log of sigma x will be sigma of minus x. So if I give these two equations, now you can compute dou L by dou B, dou L by dou W. Correct?
Mhm.
So this is how I can implement in Python. So I'm just writing this equation in Python. So minus y times w times x plus b, I'm applying sigmoid, and then I'm multiplying with y also, right? So whatever equations I computed here, I'm just making them look like code also. Okay, so this is how I can use my gradient descent algorithm to train this audio classification. I formulated a loss function and I have a lot of training data x and y and, right? So I can iterate by computing dou w, dou b. And then w, I randomly start with some values and then treat it as w0. Remember in W0, in our derivation, we started with W0 and computed the gradient and moved in the direction, negative of the direction, right? So same we do. So we compute the derivative and go in the negative direction by small amount eta. So you will see after some time, you will reach the W and B where loss function is very minimal. That means most of the training data is correctly classified. So that is what we want. So that is the end of training. Okay.
Yes, understood.
Yeah. So now let's try to, so this is an assignment. You have to implement the gradient descent on logistic regression. So I have clearly explained what is the loss equation, what is the derivatives, given the code for the derivative and the iterations for updating W and B also. Okay. So take it as a challenge. It's not simple, but everything is there. You just need to grab these portions and then put together. And before that, let me also give you an example where a simple gradient descent problem is implemented. Okay, so if you don't have this, let me share that also. In the chat, I'll put the link for this notebook also. So what I'm doing here is very, very simple. Okay, let me show that to you. So all of you see the equation a minus 1 whole squared, b plus 1 whole squared, a minus b whole squared. Say yes. Everybody can see this equation? Okay, now give me the answer. What is the optimal value of A and B at which the loss is minimal? Okay, this is the loss equation. A minus 1 whole squared plus B plus 1 whole squared plus A minus B whole squared. So you can think of A as W. That way W minus 1 whole squared plus B plus 1 whole squared plus W minus B whole squared. So something like that. So now give me, if this is my loss equation, what is the optimal values of A and B?
A should be 1 and B should be minus 1.
How did you come to that conclusion?
Sir, like I just randomly told, because if I put A equal to 1, 1 minus 1 is 0. And if I put B equal to minus 1, then minus 1 plus 1 is 0. And rest the other part is also 0. The function will return 0. So that's the minimum.
No. A is 1 and B is minus 1, right?
Yeah.
And A minus B is 2, no? The
Huh?
third term, this will become 1 minus of minus 1 plus 1, right? 2 squared.
Yeah.
Just think about it. AB 0.5 is also not correct. So how did we solve the linear regression case? Wx plus b minus y whole squared. That is our loss. Because it is simple, we said we can use calculus, right? We can use calculus and we can try to compute dou L by dou A is equal to 0, dou L by dou B is equal to 0. Is it possible here? Is it very complex? Not possible? All right. So what is the loss function? L of A comma B. Sorry. a minus 1 whole squared, sorry, b plus 1 whole squared, a minus b whole squared. Yes, somebody is computing now. Yeah. So if you just do this, dou L by dou A is equal to 0, dou L by dou B is equal to 0, you will get what are the values of A and B that give minimum value for this loss function. Okay. So when these things are not possible, when the equations are not very easy, when there is implicit relation between A and B, then you will not be able to apply simple calculus to get these values. But in this case, it is possible. You can get this. So work out later. I'll show in gradient descent how we apply this. Okay. So let us say somebody has this loss function. Okay, I'm starting from here. Sorry. So how does it look like if I plot? It's a function in 2D, right? Independent variables are 2, a comma b. I want to plot f in 2D. So this is how it looks like. One axis is a, another axis is b, the third axis is f. It has some higher value somewhere here, and then some lower value somewhere here, right? It's like a curvy plate. Okay, so higher value here and lower value here. So how do I find where is the location of the minima? So we will apply gradient descent here. So a is a tensor starting with -1, some random value. B also a tensor starting with -1. Okay, eta is small number 0.05, and I am iterating 100 number of times. So this is my loss function: a minus 1 whole squared, b plus 1 whole squared, a minus b whole squared. So if it is your classification problem or regression problem, you need to come up with the loss function. So we have seen a simple classification loss function, which is logistic regression. In this case, it is basically some hypothetical situation where loss function is somebody gave like this. Okay, now I'm computing the gradient GA, GB, gradient with respect to A, gradient with respect to B. That means dou L by dou A, dou L by dou B. Okay, so there is a autograd function in PyTorch. What it does is torch.autograd.grad. It will give gradient of y with respect to x. If you call like this, it will compute the gradient and give it to you. Otherwise, you can compute what is dou L by dou A, 2 times A minus 1 plus 2 times A minus B. Right? We started with 1 and -1 values, right? So you can have that equation. So let me write it here. So if you want to define hard code, GA will be like this: 2 times A minus 1 plus 2 times A minus B. So for simple functions, you can write directly write this. Even if it is very difficult, you have Torch, PyTorch help. You can take torch.autograd.grad. The first component is output, right? And this should be input. Derivative of output with respect to input. So if there are multiple inputs, you can give them a comma separated list. So it will give GA and GB. Once you have the derivatives, what should you do? Go in the negative direction by a small amount. So that is what I am doing. A is equal to A minus eta times GA. B is equal to B minus eta times GB. Slowly from -1 and 1 and -1, I'll make small movements. So 1 and -1 will be something like this. So this is 1, -1 would be somewhere here. Okay, 1 and -1. -1 is sitting here, no? So slowly I'll come down to the bottom of this thing here, somewhere here. So you can see the last value is 4 initially when I started, and then at A is equal to 0.8 and minus 0.8, and slowly moving towards the minimum. You can see loss is getting decreased. Whenever I make a movement, I'll see what is the loss value. I'm printing it here. Okay, slowly from 4, I'm moving down. Slowly, I'm making steps. A, B is changing. And after some point, the loss doesn't change. 1.3333, right? So that is where the minima is for this loss function. The minimum value is 1.33. It occurs at 1 by 3 and minus 1 by 3. Right? If you make dou L by dou A is equal to 0, dou L by dou B is equal to 0, you get A is equal to 1 by 3, B is equal to minus 1 by 3. So gradient descent is also able to find those values. Although in this case, analytically, it is possible to find. I'm just giving an example to verify. easily. So this is the implementation of gradient descent for a simple loss function. All right, you have any questions? All right, so this notebook is also available. So please finish the assignment of implementing logistic gradient, logistic regression using gradient descent. Okay, so the slides have equations for everything. You can even directly copy paste these functions where you want to compute the gradient. Okay, take any two class data like I created for the perceptron. Okay, define +1 and -1 and learn these W's. Start with some random W's, update using gradient descent. Okay, so this is the project you have to finish. All right, so let me quickly take, if you have any questions, we can take. We'll take 5 minutes break again. So we'll do the back propagation. Okay, 5 minutes means a little more than that. Okay, 3:55 we will meet. We'll resume at 3:55. Meanwhile, if you have any questions, please post in the chat. We can take a look at it. So I'll be briefly away to 2 minutes. I'll respond after 2 minutes. All right, back. Bhaskar Kapoor, what's the timing of quiz 2 today? So in the schedule, it is at 4:30, right? I'll try to wind up by then without disturbing that. All right. So let's get back. So we understood, started with perceptron. We have seen that it is linearly separable, linear classifier which can separate linearly separable data. Now we extended it to multiple dimensions by having multiple neurons in the same layer and then stacking more and more layers to give better and better capacity, right? That we called it MLP. And meanwhile, we take a small diversion to understand what is gradient descent, right? In cases where the loss function is not very easy, very simple to derive dou L by dou W, dou L by dou B is equal to 0 and things like that. So whenever it looks complicated, there is a mechanism. What is it? Try to formulate the loss, start with some random values of WB, or if you have some intelligent values, start with them, and then compute dou L by dou B analytically. Update Wt plus 1 is equal to Wt minus eta times dou L by dou W. Similarly, whatever is the parameter, it can be B, it can be A, it can be B, whatever, right? Slowly, step by step, you perform these gradient descent. You are guaranteed to go into local minima, where the loss is minimal. The training loss is minimal. So it looks very beautiful, right? So very, very, I would not say very simple, but very intuitive, definitely. And then you have a clear procedure now. Okay. So in case of that, that's all right. So now let's get back to MLP again. So we said MLP means it looks like this. We have a lot of layers, and within each layer also, where is this? Okay. Here. So within each layer also we have multiple perceptrons. So fine. So we have multi-layer output. Sorry, multi-dimensional output is also possible. All this is good. And now, so can we use analytical formula to compute what are the values of W's? So all these connections are W's, right? So what values of W1, W2, W3 will minimize the loss? So that is our objective, right? Because training a machine learning technique is basically finding out the optimal values for these parameters, which minimize the loss on the training data. Okay. So the purpose of looking at gradient descent is very clear now. So we are going to apply gradient descent also here for getting the parameter values for W's and P's. Right. So how does the MLP look like as a function? So let me go there. So we need, it's very clear now, we're going to apply gradient descent on MLPs. It is called backpropagation. So before that, let's see how it looks like. Okay. If loss is like this, Loss is summation of the individual losses on all the training samples. For example, I have 1,000 samples. So I have to compute loss on each sample and sum it all. That becomes the loss on the training data. For applying gradient descent, we need gradient of individual sample losses. So something like this. If sample loss on the nth sample is like this, you have to compute dou by dou wij of ln. So let's look at this term. You have multiple layers indexed by L, small l. Small l can be 1, 2, 3, and so on, capital L, if there are capital L number of layers. And also within that layer, you have I and j. Remember, if there is one perceptron, you have W as a vector. If you have multiple perceptrons in each layer, it is a matrix, right? We told that already, right? So if you are just confusing, if it is still confusing, I'll show you here. So this is one vector W, one value, one scalar B. If I increase to more number of perceptrons, each of them will have one vector. So if you stack all those vectors, it becomes a matrix, right? W is a matrix. That is why you see Wij in this term, right? Similarly, B is a vector. For each layer, you will have a B vector. Earlier, it was only scalar. Now you have multiple perceptrons within the nth layer. That's why it is a vector. So this is what we want. All our effort should be getting in these quantities. Once we have this thing, we can update random value of Wij. You just go on in the negative direction of this, right? B also same. So that is the objective. So what happens? This is what happens. X0 is the input. First layer is applied, and then nonlinearity is applied. So first layer applied, output is S1, and then nonlinearity is applied. So this becomes the output of the first layer, which is the input for the second layer. That's why the input of the weights of the second layer are applied on this. So the computation W transpose X plus B is S2. Then again, there is a nonlinearity, and so on. So when it comes to the final layer, you apply the final layer weights and biases, you will get S of L, and there is a nonlinearity which makes the output. So this is the function f of x wp. W means all these vectors, w1, w2, w3, all those matrices are simply represented with one w here. So you have to understand it is not only one matrix, it will be so many matrices as the number of layers in the network. Okay, this is a forward pass operation. So starting from input, I'm getting the output. One after another, all my layers are getting applied. Okay, so you can simply represent this in this equation. So SL is represented, computed using Wx plus B, and X is applying nonlinearity. Okay, simply these two equations will let us know the forward pass operation. Okay, so in calculus, we have a chain rule. What is it? So when you have g of f of x, you want to compute the derivative of that. So this is how you compute it, g dash of f of x, and then f dash of x, right? So this is very, very important. This is the key for backpropagation. So let me just take you to the whiteboard and show with an example what it means actually. So let's say f is log of x. So what is derivative of f of x? F prime is 1 by x, right? Let's say g is sin x. Okay, g prime is cos x. We know that, right? Let's say I have a function h which is log of sin of x. Right? This is f of g of x clearly, right? So if I want to have h prime, what is it? So what do? We do 1 by sin x, because we apply f prime first. At whatever is the argument, we just treat it as simple x and apply h. And whatever is the inside quantity, then we attend it. So now we'll find the derivative of sin x, which is cos x. So what is happening here? So derivative of f of g of x. So let me rewrite this. f of g of x. So this is basically f of x computed at g of x, f prime computed at g of x, and then g prime of x. So this is called chain rule, right? If you have more such functions, let's say you have f of g of h of x, 3 functions are there, okay? So f of g, okay, 2. So you will have f prime computed at g of x, g of h, and then g prime computed at h of x, and then finally h prime of x, right? So I'm just recapping the calculus, chain rule of calculus, okay? So this is exactly what we're going to apply in case of neural networks also. So let's just go to slides now. So when you have g and f, you just compute g prime at f of x and then f of x, right? So now you have first layer, second layer, third layer, fourth layer, and so on, right? Treat each layer as a function. Okay. So nth layer is applied on n first layer, and n minus second layer, n minus third layer, and so on the first layer, right? You have to come in the reverse order, right? Last layer is applied in the last, right? First layer is applied in the first. So now, if this is my function, how do I compute the derivative of this function? Same, f n prime computed at all the inside quantity, then f n minus 1 prime computed at all the intermediate quantity, and so on. Finally, you will get the first layer derivative, right? So derivative is here Jacobian. Remember, each of them is a matrix. That's why the derivative is no more a simple quantity, but it is a matrix. So J is simply the Jacobian of the final layer. You treat this as a function, layer as a function. You're applying the final layer on the output of the last but one layer, right? So that is what is simply applied. So pay attention, this is very, very important. And this is all there to the neural network training. If you know and understand this, you understand everything about neural network training. So this is very, very heart and soul of neural network training. Okay. All right. So let me just take you to the very specific operations, how it happens. So you take the L minus first layer to Lth layer. Okay. This is output of L minus first layer. And you apply Lth layer weight and bias, you get S, and apply nonlinearity, you get XL. Okay. So now we see what is actually happening. Right. So I want to compute dou L by dou Si. So this is a vector. So let's say ith component of this vector I want to compute. So how S is affecting the loss? It is affecting the loss through XL, right? So S computes XL and XL computes the loss. Remember, this is the output. This is the output of all the neural network. Okay, you are computing loss with respect to this. So imagine a loss equation. L is equal to yn minus this XL whole squared. Simple MSE squared, mean squared loss. Okay, so S is not directly used in computation of the loss. Instead, S computes XL, which is participating in the loss equation. So that is why what I'll do, I'll decompose this dou L by dou S as dou L by dou Xi, and then dou Xi by dou Si. Right? Because X is the intermediate link between the loss and S. Okay, loss and S directly not linked. It is linked through only XL. That's why I decompose it like this. Okay, now I know if XL is equal to sigma of Si, because X is computed by applying nonlinearity on S, this is the equation relating X and S, right? So from this, what is dou X by dou S? Simply sigma prime, right? It is X is equal to sigma of S, dou X by dou S is sigma prime of S. So that is what is substituted here. Dou X by dou S is sigma prime of S. Okay, now I still have dou L by dou X, right? So if I define L is equal to y minus xi by squared, xi whole squared, I can simply replace this as 2 times y ground truth minus x, or x minus ground truth, whatever way I'm defining the loss. It is clearly dependent on the loss equation. Clear? So that is how we can get dou L by dou S. Although S is not directly participating in loss, it is participating through xi. So I decompose like that. So this is where function of function you have to see. Loss is a function of x is a function of s. So dou L by dou S has to happen through X. All right. Similarly, if you just, go one more level, X, this one, this input quantity, how does it affect loss? Only through S, right? It computes S, which computes X, that computes loss. But anyway, we came until this. Now we know dou L by dou Si. So we don't need to go all the way back. Only one step back we can get. Okay. So you can see the relation connecting S and XL is given here. So S is computed as W applied on XL plus B. So for every step we have equations clearly now. That is why it is possible to decompose and then work out in a simple steps. So that is exactly what is happening. Dou L by dou XL minus 1, I decompose through S. Dou L by dou S by dou X. Now I have dou L by dou S here. So this quantity I can just replace from here. I only have dou S by dou XL minus 1, which can be derived from this equation. So now S is equal to sigma of W times X. So dou S by dou X is only W. So that is what is here, W. Okay. So it's a very simple but lengthy process. Process is very simple. I am decomposing the derivative through the link with which the loss is computed. So that is how we can get dou L by dou Si, dou L by dou Xi, everything. Okay. So but ultimately we need dou L by dou W, dou L by dou B, because Wt plus 1 is equal to Wt minus eta times that quantity. Okay. So we were computing derivative with respect to intermediate outputs, right? But we need derivatives with respect to parameters. So that is what we do. Same equation you can take. Again, dou L by dou W is what I'm looking for. W affects through S. So I need to decompose dou L by dou S and dou S by dou W. Okay. Earlier we found derivative with respect to X, but we want with respect to W and B. Same, dou L by dou W is because W is affecting S and S is affecting X, X is affecting loss. You just decompose suitably. So this is how I decompose it, and I reuse the previous values. Dou S by dou W is X, and dou L by dou S also we can compute from the previous computations, right? Similarly, dou L by dou B also decompose through S, and whatever intermediate values we can compute from the previous computations. So this is gradient descent applied at one layer, right? This is the output layer where loss is computed. We came one step. So you can do it how many ever steps you want to, right? From there you can compute. It's only L minus 1 and L, right? Next time it becomes L minus 1, L minus 2, and so on, all the way back. Is it clear? So I explained it for general layers, L minus 1 and L, right? So once you compute for the last layer, you can compute for the last minus 1, last minus 2, and so on, all the way to first layer. So every W will have now dou L by dou W, dou L by dou B. So once you compute all of them, we do one step of gradient descent, which is having a learning rate eta and then going in the negative direction of these derivatives. Okay. So just take a couple of seconds to see what is happening. Loss is computed using the final output. There are so many steps in between. We'll come one step at a time towards the front from the back. That is why it is called back propagation. We propagate these derivatives all the way from the output to input. What is back propagated? The gradients are back propagated. So this is why the name gradient descent when applied to neural networks is called back propagation technique. So it's gradient descent only because we want to apply negative of the gradient to take the steps in the W, but we are doing in steps, one layer at a time. That too, within one layer also you compute derivative with respect to intermediate output and then derivative with respect to the parameters W and B. All right. So this is what gradient descent in neural networks, which is back propagation. Okay. So I'll just give you another view of it. So let's say this is forward pass. Output of L minus 1 layer, applied Lth layer weight and bias, you will get SL, and apply nonlinearity, you will get the Lth layer output. It can be ReLU, sigmoid, tan H, whatever. Okay. So now once you have this, you compute the goal is to find dou L by dou W, dou L by dou B. Correct. So because once you have these derivatives, you do the gradient descent. How do we start? We compute dou L by dou XL because loss is computed directly on XL, right? That this is, treat this as the output of the network. So output minus the ground truth whole squared. Simple loss function, right? Because a loss function is clearly related to XL, you can compute dou L by dou XL. So you start from here. Yellow thing is the gradient. Okay. So everybody is clear how we got this dou L by dou XL? Because loss is clearly computed on output, we know how it is related. So I can also write it like this. So XL is my final output. So my loss is defined like this. Loss is equal to, this is predicted, minus ground truth whole squared. Simple MSE, right? Or you can have the logistic regression loss also. Anything is fine. So now I compute dou L by dou XL. It's very simple, right? 2 times XL minus Y hat. Sorry, not Y is ground truth actually. So you can represent this simply Y. So this is the quantity dou L by dou XL. So now that's why I'm not showing this, and I'm directly starting from here, right? So this is very, very important because we have the loss equation defined on the final layer output. We can simply compute dou L by dou X like this. It can be any other equation. So accordingly, the derivative will be computed. All right. From there, we start going backward, right? So S is affecting through X. So you compute dou L by dou X, dou S by dou X by dou S, right? So one step we are going forward to get dou L by dou S, and now we can compute this also dou L by dou XL because it is affecting the loss through S. So that is what is happening. I'll compute dou L by dou XL minus 1. Now we need to compute derivatives with respect to W and B. So that is what we compute. So B is affecting through S. So from here we need to get back. Again, W is also affecting through S. So we need to tag from here only. Okay. So it uses intermediate values. Whatever is the output, it also is required to compute. From these equations, it will be clear. Okay. So this is where we start from, and slowly one gradient after another we compute. So the one layer is done. Now we have to repeat the same for the previous layer, and so on. All right. So there are some observations we can make. Backpropagation is basically simple, only applying chain rule iteratively from the last layer to all the way first layer. It can be expressed in tensorial form. You can clearly see, na? So all these equations can be applied as a matrix operations, and so if you just pay small attention to each of these equations, you can clearly see all of them are, simple matrix operations, tensor operations. So then that way it can also be optimized by using suitable hardware and tensor operations. Heavy computations are with the linear operations because you need to it's a matrix multiplications, right? That is why whenever there is a linear operation, backpropagation takes more time. Non-linearity is simple function, so it is okay, right? So you can make more observations, but anyway, with because in the interest of the time, I'm just focusing only on the major points. All right. So how do we train big neural networks with hundreds of layers? So writing all these equations manually will be cumbersome, right? So these libraries like PyTorch, TensorFlow, or any other implementations, they help us get these gradients very easily. So they have mechanisms to do that. So when you properly define the neural network according to the constructs given by these platforms, you will be able to get the gradients very, very easily. For example, as I said, autograd function, right? Torch.autograd.grad. You just mention the output and give the input. you will get the gradient of output with respect to the input. So you have to define how the output and input are related. For example, in the previous, we have defined f is equal to a minus 1 whole squared plus b plus 1 whole squared plus a minus b whole squared, right? So there f is output, a comma b are inputs. There is a relation. So once you do that, you can ask to compute the gradient of output with respect to any input. If they are not related, you will get zero gradient. Otherwise, according to their relation, you will get the gradient. So this is the important function to compute backward propagation, right? So there are even more better constructs. For example, tensor.backward will give, starting from the output, it will compute the gradients of all the intermediate values. For example, if you call backward function on the loss, so loss is the final quantity you compute, right? So loss.backward, what it does is it will see what are all the independent variables that are participating in the loss computation. All the W's, all the B's, all the XL's, which are intermediate layer outputs, everything. Now, all those gradients will be computed in a single statement. So this is the beauty. You don't need to write all these, recursive equations backward, all, right from the output to the input. This will be done easily in a simple command by these constructs, right? Autograd.grad and backward. So let's see these guys in action. Okay, so now the neural network training becomes very, very, very easy because of these functions. Let's see. As I said, so without computing actually the gradients, I can use grad of L with respect to AP. So this is a simple example. Okay, so if I want to train an MLP on MNIST data, so MNIST data is a handwritten digits data. So it looks like this. The data looks like this. 0 to 9, 10 categories are there. So once you read the data, you can display the data and understand yourself. Now you have to define the neural network. Okay, so PyTorch and other libraries help you to define different layers. So linear layer means W transpose X plus B happens. And there are other layers like convolution layer, a lot of other layers will come. But for the sake of argument, let's say this is a simple MLP. We have 3 layers. First layer has 512 units. Units means the perceptrons. So remember, so let me just go back to the diagram of MLP where you can relate easily. Yes. So this is my input. So image, I vectorize the image. So the image is just being vectorized here. Oh, sorry, my bad. Yeah. So the image is 28 cross 28. So if I just make it a simple vector, it will become 28 cross 28 numbers. So 784 is the vector length. That is my input. 784 dimensional vector. Okay, we were talking about only 2-dimensional input, 3-dimensional input, right? But in this case, it is very, very huge, 784 dimensions, right? So I'm making the number of neurons in the first layer as 512. And this becomes input to the second layer. Again, I'll have another 512. And this becomes input to the third layer, which I'll have only 10 outputs. So each of these 10 represent the labels. Label 0, label 1, and so on, label 9. Okay, so this I have to define the forward pass operation also. It's very simple. Apply first layer, apply second layer, apply third layer. So that is what I'm doing. FC1 applied on X, FC2 applied, and then FC3 applied because X is being replaced, right? So sequentially you apply FC1, FC2, FC3. So I define the layers like FC1, FC, and so on. FC means fully connected. Everything is fully connected to every other thing in the input. Okay, so this is my simple neural network architecture. So I'm not spending more time on how to actually define these things and all. So based on the platform you want to use, you can look up, right? You can look how PyTorch defines neural networks, TensorFlow defines neural network architectures, etc., etc. But generally, it will be very, very similar. It will not be very different, right? You define as a class and define the layers and then define the forward pass operation, right? So you can instantiate. Once the object is class is defined, you can create an object like this. Model is equal to net of. Okay, you will have 3 layers. Input is 784, output is 512. Input is 512, output is 512. Again, third layer, input 512, output 10. Okay, so again, as I said, always we need the loss function. Loss is the key. We need to define how the ground truth is compared to the predicted value, how different they are. If they are aligned, yes, we are good. The model is doing good. If they are not very much matching, that means the model is stupid. We need to make it intelligent. We need to train it. So that is where loss function comes into picture. So for classification, cross entropy loss is used. So you can look it up. Cross entropy loss. It's very simple loss. Basically, it will compare the probability distributions and give how similar the ground truth is to the predicted value. If it is similar, loss value will be small. If it is dissimilar, loss value will be high. Okay, so that is how you define. There are other constructs also. You can look it up, but I'll focus more on the important ones. As I said, there will be one for loop for epochs, another for loop for iterations, right? So this is the main training loop. 100 epochs I'm defining, and I'm taking batch by batch. So there are multiple ways of presenting data. You can present all the training data in a single time, or you can take one at a time and show to the model, or you can go intermediate. You can take, a bunch of them. For example, 32, you can take, 64, you can take, based on your hardware, the capacity of your GPUs, etc. You can choose what is a good batch size. Okay, so from the training data, you can take the data and labels and present the data. What do you mean by present? Forward pass. Model of data will forward the data, compute the output, and then output is compared with label. So this is where the cross entropy loss is used. The predicted value is computed or compared against the ground truth output. So this is the loss. Okay, this means we traveled all the layers to the right hand side. Now, loss dot backward. I told you, remember, loss is a tensor. If you call tensor dot backward, it will compute all the gradients with respect to there are 3 different layers now. All the W1, W2, W3, the gradients related to all these things will be computed. So this is the power of the implementation tool. You don't need to do all that chain rule one step at a time. So this backward step will do that for you. It's a very simple and straightforward usage. Define the loss and call loss dot backward, and then this only computes the gradients. Now we have to go in the negative direction of the gradient, right? So optimizer does that. Optimizer dot step. So what is optimizer? You have to link like this. Optimizer is, for example, there are multiple ways of updating. So what is optimizer? I'll give you in 5 seconds. So let me just go to. So we said optimizer or update equation is like this, right? WT plus 1 is equal to WT minus eta times the gradient dou L by dou WT, right? So this is simple equation. There are some more intelligent ways of doing this. How to change the eta appropriately. Using the same value of eta all the time may not be useful. Sometimes you can be a little more intelligent and change eta dynamically, or you can work on the whole update itself, right? So every time, so there are multiple, a lot of research is happening in this area also. So there are a lot of ways of updating: stochastic gradient descent, ADAM, or ADAGRAD. So these are different ways of handling this equation. Okay, so simplest is this: WT minus eta times dou L by dou WT, right? As I said, W can be varied, or this value can be varied. There are a lot of intelligent ways of happening that. So that is where optimizer comes. So you can pick what is the update equation exactly. So that is what is happening. So if I call this as Adam, so another update rule will be applied, right? In place of SGD. Okay, so it will take a lot, another session to make the concepts of optimizer clear. That's why I'm leaving it to you only. It's a simple thing. How we update the WT plus 1 is defined by the optimizer. Okay, so that is what is happening. Optimizer.step means you take one step because I now computed the gradients and made it available. Go one step in the negative direction. Okay, so now after that you can compute the training loss. It will be smaller than before. This is an iterative process. Slowly, one after another, take data, compute the loss, backward pass, update the Ws. So this happens number of times. So you can see the training loss initially was 0.379, slowly 29, 25, 21, 19, so on. It goes down and then reaches a very small value. That is when you have to say the training is over. Okay. Or you can have a validation set and monitor the validation performance. Whenever the validation achieves the minimum loss value or maximum performance, that is where you have to stop the training. Okay. So that is gradient descent in neural networks called backpropagation. So all the neural networks, CNNs, MLP, RNNs, everything uses backpropagation for training. Okay, whether it is natural language processing, computer vision, speech processing, doesn't matter. There is a neural network. There is independent of the data type and scale of the data. Backpropagation is the algorithm is used. Okay, so that's why pay close attention and try to understand all these steps. And implementation is simple. Basically, in this loop, you take each data or a bunch of data, pass it through, compute the output, compute the loss, and call loss.backward. Simple. And everything else is just beautification. So how to display, how to download the data. There are some ways how to handle the training data. Can we sample it better? Things like that. Okay. So I make this also available, this notebook also. So please pay attention. Look at all these intermediate cells and understand what is happening, and you can apply the same logistic regression problem using neural network also. Okay, so I'll stop here, and if you have any questions, quickly one question probably, or if there is no time, I'm also fine not taking questions, but if you have any questions, we can take it. Yeah, so because this is time constraint, we could not go through in detail, but I tried my best to focus on the important concepts and important constructs. Yeah, so that way, make use of all these notebooks and look at the assignment. So finish that assignment. Yeah, so no need to worry about Python. Okay, so these implementations are not very difficult. For example, I myself had no computer science background. Okay, so this encourage yourself. It's only the starting trouble. Once you cross that over, it's simple. Okay, all right. Yeah, if there are no questions, I'll stop here. I don't know the name of the person. Kaushik ji?
Konda sir, it's Biplab here.
Oh, Biplab, sorry. Yeah, so I forgot your name. I'm sorry. Yeah, so I'm done. You can take it forward from here.
Okay, sir. So dear participants, now the session is over, but there is a MCQ. All of you are requested to visit the link which we have shared in the Google Drive with you all. There, the link for MCQ is there. The link is active now. You can appear in the MCQ. It will be of 15 questions and it will be of 30 minutes. All questions are not compulsory, but you are requested to try to solve each and every question. And there may be more than one option in few questions. The hint has been given to all of you there.
Sir, excuse me, can you please share that Google Drive link again in the group or in mail?
Yeah, I am just sharing it in the chat box.
Okay, yeah.
Is it visible?
Yeah, sir. It's visible.